Okay, morning, gentlemen. Morning. Jim Campbell's just the person you had yesterday. He's just asked me to give you a bit of information from yesterday about icing. So what I'll do is I'll put it in the chat, and so you can actually see it there. So it's basically, it should be firing out towards you now. Can you all see that in the chat box? Hello, can you hear me?
Yes, I can see.
So it's basically, he's talking about something about, you were talking about anti-icing yesterday, and he's basically just clarifying that fast cycling electrical de-icing is for light icing and slow is for heavy icing. Okay? Somebody asked that question yesterday.
Okay, thanks.
Okay, does that make sense to you all, gents?
Yes, thank you.
Good, that's good. Right. Right. So we think that's everyone here. There's about 15 people, is there? Yeah, okay, we'll make a little start. Okay, people come in. Now, please, gentlemen, if you have any questions, please ask, okay? Either put your hand up or just come in and speak, okay? I'm quite happy to answer any question. Oops, somebody else would come in. I'm quite happy to answer any questions, okay? I'll take you through the notes. Oops, keep coming in. We take you through the notes. If you listen to what I'm saying, okay? This is quite a compressed course, so I'll be literally picking out the important bits for each system and how they work, okay? So you just listen to me, you can't go wrong. Now, give you a little bit about myself, okay? Before starting this job, I started as an old-fashioned aircraft electrician. 1980, long time ago, okay? Got damaged knees, so I can't work on the tools anymore. So I had over 26 years working on the tools. So I've actually been where you are. And I started, just like you, or most of you, as a mechanic. So I've actually been where you lot are, okay? I'm going to get this right. Dig Amber, you want to ask a question? Just you put your hand up.
No. Just I push it mistakenly.
Okay, that's fine.
Yeah.
Okay, I'll just put your hand down. Okay, lovely. So I have actually been where you are. I have actually started as a mechanic and worked my way up. Okay. Being an aircraft electrician and having to do the avionics conversion later on. The instruments, that was my main trade. So was the electric, so was lighting, so was navigation, or the compass navigation aids. And also converted to do some of the avionics. So what you're getting from me is from someone whose actual trade it was. So I actually worked on these systems for 26 years. The next thing is, I am a helicopter. I was in helicopters all my time. Okay, is there anyone there? Helicopter engineers?
A lot of our friends are helicopter engineers. Yeah.
Oh, so Chris and who else? Naveen, Dambat. Oh, lovely. So we've got some helicopter engineers.
Yeah.
Remember, helicopter and Rajesh. Remember, helicopter engineers are the best aircraft engineers because they keep breaking and vibrating to death. Okay.
Thank you.
Okay, thank you very much. So just put your hands down, please, ladies and gents. Or gents, no ladies in this class. So, how this course is going to work, okay? I'll be going through it, and I'll just give you a quick outline of what we're planning to do. Now, you're all so you're here for the whole 9 days, okay? The first 3 days we'll be talking about instruments. The second 2 days we'll be looking at the basic avionics systems. I know you're all mechanical, and there's this big fear about avionics systems. Don't. The title gives it all away. It's basic avionics. Okay, it's basic avionics. There's 1 or 2 little bits that are slightly higher. I'll take you through that when we come to them. The next 3 days will be power, and the last day we'll go through lighting. Okay, lighting's not complex. Okay, so that's my sort of background. Okay, I have been to Nepal once. I was there about 2 years ago. I was there in Kathmandu doing a course. Well, at NAT in Kathmandu. So I have been there. Lovely city. Spent a lot of time in the Garden of Dreams. I thought that was a very lovely place to go and sit and rest in an afternoon. Now, please ask questions, okay? If you're not too sure. Now, I've actually sent Sanjeev some sheets for you to help you to revise. So hopefully he'll send them out to you in your case this afternoon. If he hasn't got them by the end of the day, can you let me know, and I'll send them. So if somebody gives them their email address, I'll send them the sheets, and you hopefully if you can send them out to one another. Okay. Right, so the first bit we're going to look at today is basic instruments. Now, the advantage you have got, gentlemen, over some of the young students we have got, 1, you know what an aircraft looks like. 2, you know what a cockpit of an aircraft looks like. You'll have listened to other engineers talk about certain systems, okay? Talk about certain systems. So you'll have a bit of an understanding when I'm talking about, when I mention things, you know what it means. Instruments, okay? Basic instruments. As most of you know, we've only been flying for what? Was it 1903 was the Wright brothers when they first flew? And their aircraft, the Kitty Hawk, flew a couple of 100 meters. Okay, first powered flight. Did anyone tell me what instruments they had on the very first flight? Anyone know? They didn't have any instruments. They had a little bit of ribbon attached to one of the struts. And that just gave them the direction of the wind. They knew about that in aerodynamics, and knew about that because there was gliders at those times, but that's all they had. And it's one of these things, as technology goes on, one of the worst things, gentlemen, about the human race is technology advances through war. Come to the First World War, we had little aircraft, not very big, not very far, not very fast. But as technology, the ability to shoot the aircraft down meant they had to be further away from the battlefield, which basically means rather than just flying a mile or a couple of kilometers, we're now having to fly many miles. So now they had to have airspeed, navigation, compass systems, height. So basically the technology advanced through warfare. It's sad about human race, but that's the way it is, okay? So what we're going to look about today in the first part is requirements for instrumentation. Okay, so we're going to look at the requirements. Unfortunately, we don't have time to show you that video. I'll do it at the basics. This is what we're going to look at today. So hopefully, at this part, we'll look at the ICAO. Okay, you all happy what ICAO is? Is the International Civil Aviation Authority, the world's regulator for aviation. Okay, you've got your national authority, the Nepalese CAA. In UK, we've got the CAA. In Europe, they've got EASA. In America, we've got the FAA. But they all come under the umbrella of ICAO, the International Civil Aviation Authority. Then we're going to look at the basic instruments of flight. Okay, we'll look at the basic instruments. We'll find out what they are and what they do. Okay, we'll find out what they are and what they do. So we're going to have things that's going to be pressure related and navigational related. Okay, and hopefully by the time you finish this, we will be all good. So this is the first thing. As I said minutes ago, that the International Civil Aviation Authority are the authority for all the aircraft, all aviation related matters. Okay. And they've got regulations for the whole world. But early on in aviation, every company who made an aircraft did everything themselves. They made their own regulations, their own specifications, and they put their instruments in the aircraft where they wanted. And not every aircraft had the same instruments. So you couldn't easily go from one aircraft to another. And that didn't matter because in aviation, in early 1930s, early 1940s, it didn't matter because there wasn't much. If you were able to fly, you usually flew one aircraft. But when it came to the Second World War, when Britain and Germany were fighting, and Britain was nearly defeated, they had to take a lot of pilots from the bombers and the flying boats and put them into fighter aircraft. And they realised they might have spent 2 or 3 years on an aircraft with its instrumentation set out where that manufacturer put the instruments. When they went into another aircraft, the instruments were all over the place. Okay, and you've all done some sort of human factors training in the past. You know, repetition memory allows things to do things quicker. So what happened with RAF, they actually made a requirement that all the aircraft instruments, the navigational performance instruments, or what we now call the flight instruments, were laid out in a specific way on all their aircraft. And this became now the standard. This is the standard now you're going to find in all the aircraft. So they've laid down what types of instruments are in your aircraft and where they go, and the standards they must be manufactured to. Okay, the standards they must be manufactured to. So that's the first thing they said there. They say, that's the bit there, said be conformity of design, development, operation. They set the standards that be manufactured. And it said there they laid down the airworthiness standards for instruments. Okay, laid down the airworthy standards of instruments. Give you an example. Kathmandu. Okay, Kathmandu. You're in the valley. It's quite relatively hot and dry most of the time. So if I was to build an aircraft in Kathmandu, I would build it to what Kathmandu, the area around Kathmandu, is like. If I was to build a aircraft in Scotland, I would build it to what it's like in Scotland. Cold, wet, grey. And that's fine. As long as it stays cool, wet, grey, my instruments are perfect. Let's go back to Kathmandu. Okay, until I went there, my view of Nepal was the Himalayas, all mountainous and snowy. Having now been there, I know there's the mountains and snowy, there's the valley, and then you go to the hot, humid place by the Indian border. So now if I base my aircraft instruments round the Kathmandu Valley, and I fly into the Himalayas where it's high, cold, the atmosphere is different. So my instruments would be accurate in the Kathmandu Valley. They wouldn't be very accurate up in the mountains where it's cold. And as we all know now, your aircraft can fly all over the world. Okay, you can fly from Nepal to Dubai, Nepal to Delhi. So your aircraft are now flying around the world. The atmosphere, the weather, the height of the airfields all change around the world. So what they've actually done, they've actually set down standards for my or your aircraft instruments in your aircraft. So no matter where your aircraft is in the world, its instrumentation hopefully will be very accurate. Its instrumentation will be very accurate. Now here's an old aircraft. Okay, old aircraft. It's got old analog gauges. Now some of you are working on aircraft that have probably got EFIS, you know, the old TV screens. I take that's correct, gentlemen. Some of you are working on aircraft that have got the old electronic flight instrument systems, the old 6 TV screens. Is that correct? Yeah? Anyone? Okay. Some of you might be still. Pardon? Glass cockpit, yes. That's it. Glass cockpit, electronic flight instrument systems. Some of you might be still working on aircraft that have old-fashioned instruments. At the first part, what I'm going to say to you here is, when you've got a glass cockpit, basically a TV screen, it's providing a TV picture. Here, we've got old analog gauges. So when everything moves, it moves a pointer. What I'm going to say to you is the majority of the systems we are going to talk about provide the exact same information or how it develops its information, but rather than moving a pointer, it puts that information onto a TV screen. So how it senses any changes is very much the same. How it's pictured is different. Now, if you look at here, I think this is an old Dakota cockpit. You can see this gauges marked up in this white area. Okay. That's what we call the Classic 6. Okay. In theory, any pilot should be able to fly an aircraft from London to Kathmandu, or London to Dubai, or London to New York using these 6 basic instruments. Okay, I'll just point now. Yeah, so just look at these here. We'll look at these here. The one we've got, this one here, my airspeed. Okay, airspeed. It's a pressure instrument that gives me airspeed, and when we talk about airspeed, it's the airflow over the flight over the wing, okay, or the fuselage of the aircraft. Next one we've got here is called an artificial horizon. It gives the pilot the pitch and roll of his aircraft relative to the Earth's surface. It's a gyro instrument. Okay. Next one here is my altimeter. Okay. It's a pressure sensing instrument. Okay, we'll come into this a lot more later on. It's a pressure sensing instrument. And one of the things we're going to find out is when I go higher, atmospheric pressure changes. So this altimeter is going to sense the change in atmospheric pressure. This one here we call the vertical speed indicator. It changes, again, it's a pressure instrument. So it's going to change it measures the change in the rate of pressure change. And that gives us how fast we're climbing or how fast we're descending. Then we have a compass, a navigational instrument to give us the direction, okay, give us the direction, and we'll look at what direction it can give us. And the last instrument is something called a turn and slip indicator. We'll look at that a lot later. Most modern aircraft now, you will not see a turn and slip indicator in the cockpit. You'll probably find it more in smaller aircraft. Those who are working in smaller aircraft. Those who are working in smaller aircraft will see this. But what I'm going to say to you, gentlemen, the information that provides is used by most aircraft in a Pacific system, and we'll be looking at that later on. Okay, we'll be looking at that later on. There's a small private aircraft. They've still got the basic 6 instruments. Is anyone working on small private piston engined aircraft? No. Somebody going to say something?
Yes.
Yes, we can hear you.
Okay. Oh, right. So is there any people working on small piston engine private aircraft? No. Nope.
Nope.
Nope. So most of you will be working on this type of aircraft. This type of cockpit. Yep.
But not Boeing, it's Airbus.
Yeah, Airbus, yeah. But the screen, but the instrumentation is the same. You've got the 6 screens. Okay, we will be looking at that later at the end of the. We've got the 6 screens. That's got all my navigational information. Sorry, that's got all my flight information, keeping the aircraft in the air. This one here's got all my navigational information, and these ones here, I've got all my engine information, which is the exact same as this. And there's my engine instruments there. They say pilots prefer this. Well, maybe they do. And they find this hard nowadays. As you've all know, pilots, they tell you they're in the top 10% of intelligent people in the world. So if they're that intelligent, why do they find that easy, but that very difficult? If they're intelligent people, they should be able to work that out. In fact, they used to fly across the Atlantic and go from London to Australia using those instruments. So have pilots become more stupid? I'll leave that for you to work out yourselves. Okay. So that is what we're going to end up with. What I'm going to say to you, gentlemen, most of the inputs into here, how the information that these gauges get is very much the same as this, but it's now a TV picture. Okay, it's now in a TV picture. But we will look at all the instruments as we go on. So that's there. Now, as somebody mentioned, you all work, or most of these work on Airbus, except for the helicopter engineers. They're good engineers. But you see, you're working on Airbus, and you quite rightly said that was a 737 cockpit. But those who are on Airbus, can you just confirm that the cockpit electronic flight instrument system, the glass screen, the TV screens, that's the same or very, very similar to what's in an Airbus? Can you confirm that for me, please? Hello?
Very much similar.
Very similar. So it's got 6 TV screens. Yes?
Yes.
Yeah. So why did that happen? Because we all know Airbus and Boeing don't like each other. So why have they got cockpits very, very similar? Because what had happened is ICAO have set standards and requirements for the glass cockpit. Just to set down requirements and standards for an old analog cockpit. So they've set the standards. Okay, they've set the standards. So that's why when you go from an Airbus to a Boeing to McDonnell Douglas to a Lockheed to Bombardier, it'll be laid out the same for glass cockpits. But if it's an older aircraft that's got analog instruments, it will be laid out the same because ICAO set down the standards, beg your pardon, and requirements for cockpit instrumentation. Okay, so that's the first thing to remember. Who sets the standards? It is ICAO, International Civil Aviation Authority. And what they have said, okay, what they have said is this here. They've given regulations. Now, these regulations are big, okay? There's lots, they're quite complex. We're going to break them down to a few little regulations. Those regulations will go into your CS25 for your big aircraft, your certificate of service. They're going to, so ICAO tell them what to do. When the Airbus or Boeing write the CS for their particular aircraft, they're taking that information and they're putting it in to their regulations. Okay. So the first thing it says here, instruments shall be located so that they can be used by the appropriate crew member. Okay. Why don't they say pilot? Okay. Why don't they say pilot, not crew member? Remember I said these standards were made in late 1940s, early 1950s. And in those days, we had two pilots, we'd have a navigator, and we would have a flight engineer. Most aircraft now don't have a navigator. And only few older aircraft, and usually the cargo aircraft. I know that cargo 747s still have a flight engineer. So as this regulation is for all aircraft, that still stands. So basically, they must be located so it can be used by appropriate crew member. So the pilot will need to see things that keep him in the air. He'll need to see the engines, and he'll need to see navigation instruments. Okay. The next thing it says, they must be illuminated to aid viewing. Okay. Aid viewing. Why don't they say must have lights at night? Because there's certain weather conditions when it's like, if it's foggy, it's dull, then we need lights. Okay, so it's obvious we need lights to be able to see the instruments. Flight navigation and power plant instruments are. Okay, so flight keeps it in the air, navigation gives it direction, and power gives them the thrust to keep the aircraft in the air. Okay. The first thing, it says they have to be plainly visible. Okay, plainly visible. Now remember I said right at the beginning, aircraft manufacturers in the early days of aviation put their instruments all over the place. And we've got an old helicopter just about to be replaced, thank goodness, where actually the airspeed indicator, the pilot had to look down and to his left. His airspeed indicator, as we all know now, you've probably done a bit of aerodynamics, you need to know your airspeed so you don't stall. So why put it somewhere where the pilot has to take his vision away from the direction he's flying? So they've actually now stated they have to be plainly visible so the pilot can see them. They have to be in line of vision when he's looking forward. Okay, again, it's a human factor. When you're just moving your head up and down, so looking out the cockpit window, looking down, it's one movement. Your head can do it and your eyes can change focus from two areas quite easily. But remember I said with an old helicopter where the airspeed indicator was down and to the left. So now I've got to look down and left. As I'm coming from there to there, I'm changing direction 3 times. And my focus is changing. And the light looking outside compared to inside the cockpit, looking down in the cockpit is going to be darker than looking at natural light. So my focus, my vision, because of the light changing, I'm going to have problems. It's a human factor. So he said there, has to be in line of vision when looking forward. Next thing they say, it has to be symmetrically disposed about the vertical plane of the pilot's vision. That's a lot of big words, okay? Even for someone who's got English as a first language. But what it means, if we go back to this, so here's my pilot. There's my classic 6 instruments. So the first thing is, there's the center line of the aircraft. And if you look here, the gauges are symmetrical down the centre line of the aircraft. So what's on one side is on the other. But also look here. That's the centre line in front of the pilot's vision. So the attitude indicator and the compass are directly in his line of vision. And then we've got the other gauges left and right. And it's the exact same on this side. So if you're between a pilot and a co-pilot, you might swap sides every flight or every couple of days. You can now see, if you know that to the left of the attitude indicator is my airspeed. Doesn't matter what side I'm on. So now when you have to go and look for the airspeed, you're flying in that aircraft, and in fact, you're flying in any aircraft, you know it's always going to be there. So that's the thing there. It's symmetrical. So basically, the instruments are the same either side, no matter where he is. And it says again here, all power plant instruments, or all engine instruments, grouped so they can be seen by the appropriate crew. Going back again to this word crew, and I go back down to like the cargo 747s, where they've still got a flight engineer. The flight engineer, his job is to monitor the instrumentation. Okay, when we look at flight instruments later on, you'll actually, when you look at you do mod 5, you'll find out a lot more about the instrumentation, the ECAM and EFIS systems. And if we know there, they automatically, anything goes wrong, it puts up a warning, up comes the information, and it tells you what's wrong, and it also tells you what the pilot has to do. Back in the old days when a flight engineer was sitting looking at all those instruments, he was constantly monitoring instruments to see if anything went wrong. And he would tell the pilot what to do. So basically, that is still there. Oops, that is still there. Okay, because we've still got some aircraft flying with a flight engineer. And next thing it says, in multi-aircraft power plant instruments for each engine located to prevent misleading information to what engine they relate to. Okay. So, what does that mean? Get my pad up working. Right, here's our normal two-engined aircraft. And we'll call that one, and we'll call that 2. So we could say that's N1, N2, we'll call that temperature, and we'll say that's pressure. In reality, this is quite easy because there's my centre line of my aircraft. So the engine on the left, those gauges left of the centre line are for that engine. To the right, that is the engine on the right. It makes logical sense. Now let's look at a multi-engine aircraft. Now, in the olden days, some aircraft manufacturers called that 1, 2, 3, 4. Other aircraft manufacturers called that 1, 3, 2, 4. And again, it can be confusing. So what they've actually said is, right, we have to be logical. Okay, so let's get rid of that. So now, there we go. Logically, everything on the left side, 1, 2. Everything on the right hand side, 3, 4. We don't have to worry about it. So they've actually basically logically given the aircraft engines a logical numbering system. Okay, and of course that will be an N1 on that engine, N1, N1. So basically the pilots have got a logical way of looking at their engine instrumentation. Okay, they have a logical way of looking at the engine instrumentation. Right, so that's where this comes in. In multi-engine aircraft, power plant instruments for each engine located so prevent misleading information to which engine related to. So they've made it logical for the pilots. Okay. So looking at it, you think about it logically that all instruments have to be plainly visible and in front of the pilot when he's looking forward. So he just has to go up and down. And they have to be symmetrical, so logically the pilot knows that instrument's there on this aircraft and that instrument there on that aircraft. And all multi-engine aircraft, the engine instruments are logically grouped so we don't mislead it. So basically, N1 will always be the top on all 4 engines. And working your way down, and it'll be 1, 2, 3, and 4. Okay. And that is the exact same how it's going to be in a glass cockpit. You can look at your engine instruments. That'll be number 1 engine. That'll be number 2 engine. Okay. We'll go before we just go for a quick break. Okay. So I know how bad it is sitting in front of a computer screen for a long time. Your eyes get sore, your back gets sore. You need a cup of tea as well. We're just going to look through the basic instruments, okay? And again, we call these the classic 6. The first one here, okay, we call that, come on, that's my ASI or airspeed indicator. This one here is a gyro instrument. I think our notes call it an ADI, airborne direction indicator. If you're like me, you know it as an artificial horizon. Next gauge here is my altimeter. It gives me my height. It gives me my pressure height. We'll talk about that a lot more as well this morning. This one here again is another pressure instrument. It's my VSI, vertical speed indicator. Gives me my change in height up and down, or the rate of change of height. And this is my compass. Will give me my direction. And this one, some of you probably have not seen before. This one is what's called a turn coordinator. You can see it there. There's two different instruments we'll talk about. A turn coordinator will realise that we need this, or the information this provides, because in certain scenarios, the compass becomes very inaccurate. And this will tell me how many degrees per minute I'm turning. Okay, because if you don't know where you are, if you know how many degrees you're turning, you can do a quick time, speed, distance calculation. You work out how far you've turned. And again, that's another gyro instrument. Okay, so that's either called a turn coordinator, or the other instrument we look at is called a turning slip indicator. Okay, and the other one, so we called it the classic 6, and then the basic 7 we have what's called the T shape. Okay, they are the instruments that you really do need to fly. Airspeed, attitude, altitude, and compass system. Okay, compass system. So please remember what the classic 6 are, the 6 basic instruments, and what the ones you really require to fly. Okay, airspeed, attitude, altitude, and direction. Okay, direction. What we say, gentlemen, that will be going down for nearly 50 minutes. We'll go for oops, somebody's in the kitchen. We'll go for a 15-minute break. Get up, have a stretch, get a cup of tea, get some natural light into your eyes. I know it's nearly getting dusk where you are, but try and get up, get stretched. Okay, and we'll come back in 15 minutes. Are we all okay with that?
All
Yes?
okay, Ian.
Okay, I will see you in 15 minutes. Okay.
See you.
Right, ta-ta.
Tata.
सुपर गिरधारी वाला था तो था हाँ
Hello, gentlemen, we all there? Hello, can you hear me?
Yes.
Yes, we can
Okay,
hear
thank
you.
Yeah, gentlemen, put your hands up if you're all back from your cup of tea. Did you have a nice cup of tea?
Yes.
Lovely. Okay. Right, let's get a start. So just going to highlight the, oh, yes.
So you will be highlighting in our notes also?
Yes, you can highlight in your notes as much as you want, okay?
So
Okay,
you will be telling to highlight.
You just listen to what I emphasize, okay?
Yeah.
You just listen to me, okay?
Yeah.
Right. So basically, we look at the basic, the little diagram here. Just to highlight again, airspeed indicator. It's a pressure gauge going to give you the speed of the air across the aerofoil. 2, attitude indicator, also known as an ADI, airborne direction indicator, is a gyro instrument. It will give me the pitch and roll of the aircraft. 3, altimeter. Altimeter will give me the height, a pressure height. We'll look at the 3 different pressures we're going to use. 4 is a turn coordinator. It's a gyro instrument, and we use it, or the information in modern aircraft is used because the compass in certain conditions, okay, like the compass in certain conditions doesn't work very well. There's my compass, gives me my direction. It's a gyro instrument. And then I've got my, oops, vertical speed indicator, another pressure instrument. And that will give me my rate of height change, either climbing or descending. There's all the instruments we've got there. Okay, so it makes what we said. Right. Going to look at some pressure. Okay, going to look at pressure. As we're walking around, okay, as we're walking around, or let's say standing still. Okay, standing still. Above me is a column of air. Right above me is a column. It goes from ground level into all the way out to outer space. And we've got molecules of oxygen, nitrogen, all the other gases. They all have a weight, and that weight is actually above me. Okay. And that weight, okay, is we can call that as a pressure. Okay, that's a pressure. And we're going to use that pressure to give us our height or change in height. Okay, change in height. And we're going to call that static pressure. The next pressure we're going to talk about is something called pitot pressure. You got it from your pitot mass. It's a combination of the pressure caused by the weight of the air above me, also the pressure caused by the resistance of the air on the aircraft, caused by the speed as it goes through the atmosphere. Okay. And we're going to be looking now at what's called the pitot-static system. Okay, the pitot-static system. Remember I said the airspeed indicator, the vertical speed indicator, and the altimeter are pressure instruments. We're going to come back to this a bit more in depth later on, but just be aware that we're talking about pressure, okay? We're talking about pressure. So the first gauge we're going to talk about, okay, the first gauge we're going to talk about is the altimeter. Okay, that gives us the height we're at. Or I've got to emphasize again, it gives me a pressure height. Okay, gives me a pressure height. And the first thing we need to remember is the higher I go, the less air it is and the less pressure. So that column of air so here's me on the ground. Yeah, standing on the ground. Go, I've lost a lot of weight. But above me, I have that column of air. And it's putting a force on me, a pressure. But now if I go further up, you can now see I've got less of that column of air above me. That means I must have less pressure. Okay, so basically what I can actually state is when I go up in altitude, pressure goes down. Okay, so that's the first thing you need to be aware of, gentlemen, is when I go up, the pressure above me goes down. And that pressure is called static. Okay, So that column of air, the pressure caused by that column of air above me is called static pressure. And that's the shortened version for pressure, PX. And our altimeters work on that pressure. They work on static pressure alone. We're going to look at, okay, the altimeters. There is a very basic one. Yep, very basic. More complex, even more complex. But they all work on that basic principle. As I go up, pressure goes down. Okay, as we go down, pressure goes up. And that's what we call static pressure. Before we go into look at that, we need to understand the pressures that are affecting my altimeter or my aircraft. So, I know this is a picture of Europe, but it doesn't matter where you are. It could be one side of Nepal to the other. There you go. About there is New York, the Big Apple. I am about here, okay, in Scotland. Now look, if I'm flying across the Atlantic, you can see the atmospheric pressure, okay? Well, look at this here. These are basically pressure lines, okay? So that's the atmospheric pressure. And you can see here it starts at 1020, goes all the way down to about 10.4, 1010, 960, 992, then starts to go up and then it starts to go back down again. So now that's pressures at sea level, okay? That's pressures at sea level. But sea level is our datum, okay? It's our starting point for our column of air. So now, if I have a pressure, a static pressure, well, let's say that one there, round about me, is 1,000. If I go up, that pressure is going to go down. But if I now go back to New York, I have a pressure of 1020 at sea level. But if I go up, the pressure is still going to go down. But for each individual height, we're going to have a different pressure in Scotland than we will at New York. So now going back to, if I had my aircraft only built to fly around Scotland, I'd just get my instruments just for that pressure. If I want to fly just around New York, I'd just get my instruments to work round that pressure there. But as you can see now, the pressure changes as I start to go across the ocean, go across the land. So we need to compensate for changes of pressure. Because remember, my altimeter gives me a pressure height. And we also need to compensate for what happens as we go up. And there's some pressure problems we can't get rid of, but we've got a solution for it. And this is what we're going to look at this morning. Okay. So the first thing about an altimeter, okay, it's an aneroid barometer, okay. Aneroid stands for without air. Why is it air? And it says there, altimeter measures pressure. And to measure pressure, you've got to have a reference. Okay. Now you've all done physics. You've all done physics. Hopefully you've all done physics, and you know that if I have set volume of air and I heat it up, the pressure inside there is going to go up. So what we've actually got to do is have a reference. So we can't pick a particular pressure, 10 psi, 1 psi, 13 hectopascals. We have to have something that's not changed by temperature. And the only thing it's not changed by temperature is a vacuum. So the reference for my altimeter is a vacuum. Okay. 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 The reference is a vacuum. Next thing we need to remember, gentlemen, this bit. Height is inversely proportional to pressure. And all that means, the higher I go, the higher in altitude I go, the lower the pressure, okay? I go high, low pressure. Okay, so just remember that. What is the relationship between height and atmospheric pressure? The higher I go, the pressure goes down. When I start to descend, pressure goes up. Okay, we've already mentioned that ICAO makes that, and we'll look at the standards they give us. Right, the first thing we need to think about is these standards, okay? And as I mentioned earlier on, depending where I am, will depend what my today's pressure. Here it's very, very cold, it's low pressure, and it's raining. Kathmandu, I take it Kathmandu's fairly warm and dry today. Yeah, so I'll probably have some sort of high pressure. So now we need to think about, again, if I'm in Kathmandu or in Scotland, my altimeters will read differently. Okay. So what we have to think about is something called the standard atmosphere. ICAO came up with this standard atmosphere. So now every single instrument, aviation instrument, is made to the standards laid down by ICAO. Okay, and we call that the standard atmosphere. Okay, and the first thing to note about the standard atmosphere is, it's measured from average mean sea level. Okay, we pick a point of a latitude of 45 degrees. Okay, because that's the average between the equator and the poles is 45 degrees. And we put it from sea level. And why we say average means sea level, you've got tides, low tide, high tide, waves, etc. So ICAO have got this theoretical sea level. Okay, and it's called average mean sea level, and it's 45 degrees north or 45 degrees south. The next thing is, we need to have a standard pressure. Okay. And that's my standard pressure, and it has just changed to hectopascals, HPA. All they've done is change the units. The measurement's the same. It's just when they moved ICAO from America to France, they just changed all the units. So the standard atmosphere is average mean sea level with a set pressure of 13.25 hectopascals. And as I just pointed out earlier, that pressure changes with temperature, we actually have a standard atmosphere. So all our instruments, okay, are built where the standard of build is done at 15 degrees. So it doesn't matter whether you're in cold Scotland or warm Nepal. If you build aircraft instruments, they're made to the standard atmospheric model, okay? And the things to remember are the datum point is average mean sea level, which is 45 degrees. The pressure is 13.25 hectopascals at a temperature 15 degrees centigrade. Okay, please remember that. You are required to remember the standard atmosphere. Average mean sea level at a pressure of 13.25 and a standard temperature of 15 degrees. Okay, 15 degrees. The next thing to look at is how altitude and temperature and altitude and pressure if you look to the left-hand side here, you can see as I go up, pressure goes down. Yep, and we talked about it already. But also we said here, if I go up, temperature goes down as well. And up to 12,000 meters, okay, is 36,000 feet. And what happens is here, up to 36,000 feet, the temperature goes down. And when it gets to what we call 36,000 feet, it changes and it stays at minus 56.5 degrees. We live in the troposphere. The next level is called the stratosphere, okay? The little bit in between, I think I've got a diagram of it. Okay, is called the tropopause. So at 36,000 feet, the temperature, according to the standard atmospheric model, stays at a constant minus 56.5 degrees, okay? Minus 56.5 degrees. So remember those bits so far. Standard atmospheric model, we'll look at another couple of bits we'll look at, but we'll look at this at the moment. Is measured from average mean sea level with a standard pressure of 13.25 hectopascals at a temperature of 15 degrees centigrade. That temperature will go down constantly until it gets to 36,000 feet, or the tropopause, when it stays at a constant minus 56.5 degrees. Okay, are we all happy on the standard atmospheric model? Can you put your hands up, please, on your computer if you're happy with that? Everybody else all happy? Is everyone else happy? Because quite a few people not put their hand up. Or rephrase that. Anyone want to ask any questions on it?
Yes, Mr. Lloyd.
Yes.
Yes. Can you please explain what this 36,000 up to that height it belongs to tropopause? You mean to that?
Yes.
So on that tropopause, is temperature remain constant to 56.5 degree minus?
And it stays basically in the stratosphere. So you've got the tropopause, sorry, this troposphere, which is where we live. If you think about Mount Everest, okay, that is where we go from the place where we can live, breathe, just. Above that, we go into the stratosphere, but there's a little band between the troposphere and the stratosphere. And so that is where this constant 56.5 degrees. So when you go in the all the way through the stratosphere, the temperature remains constant. Okay. So when your aircraft are flying at 36,000 feet, outside, according to the standard atmosphere, it will be constant minus 56.5 degrees. Okay.
Okay. Thank you.
Yeah. We'll have a look. We could talk about this a little bit more later on.
Okay.
Okay, good. Right. If you, like me, you were brought up with millibars, okay? Millibars. And you'll probably find a lot of older engineers and pilots, they talk about pressure as millibars, okay? The new temperature units is hectopascals, HPA. The values haven't changed. So 1,000 millibars is the same as 1,000 hectopascals. They just changed the units. It cost the aviation industry thousands and thousands of dollars to change all the publications. Okay, that's that bit there. If you just remember, 1 millibar equals 1 hectopascal. Okay. Those who work in some older aircraft or some American aircraft, they measure everything in inches of mercury. Don't worry too much about that. We ain't going to be covered. You're working on more modern aircraft. But this is another bit about the standard atmospheric model, okay? A change of 1 hectopascal at sea level is a change of 30 feet, okay? Please remember that. We're going to look at this now. Okay, I'll get into the next slide. Right, so basically, change, oh, that's badly, of 30 feet, okay, equals 1 hectopascal, okay, in pressure change. So every 30 feet I go up, the pressure changes by 1 hectopascal. So what we've also got to remember, gentlemen, is if I go up, okay, so my altitude goes up, my pressure goes down. So now every 30 feet I go up, my pressure, my atmospheric pressure, my static pressure goes down by 1 hectopascal. So let's have a quick look at that. Average mean sea level, okay? And that standard atmosphere is 10, 13.25 HPA and 15 degrees C. So we'll call that 0 feet because it's sea level. And let's call this, we've got a little airfield and it is 300 feet above the sea. And that's 300 feet elevation. So it's above by 300 feet. So if the pressure is 1013.25 at sea level, what would be the temperature? Sorry, what would be the pressure at that airfield at 300 feet? So let's have a look. I know the change in height is 300 feet. I now know that for every 30 feet, there's a change of 1 HPA. So I need to find the pressure change. I've got 300, so I'm going to divide that by 30, and that equals 10. So my pressure has changed by 10 hectopascals. So now I can say what would be the theoretical standard pressure at my airfield. It must be 1013 minus 10, and that will be equal, oops, 9, let's say 9, hold on. So now my pressure must be 1003 hectopascals. Why is it 1003? Well, we know we've worked out the change in pressure, which is 10. And we now know if I go up in altitude, pressure comes down. So now if I have gone from sea level to 300 feet above sea level, the pressure's gone down to 1003. Okay, so please remember that little formula. 1 HPA equals 1 hectopascal change in height. If I go up, pressure goes down. If I go down, pressure goes up. This is why it matters. Okay, this is what the pilots will look at before they take off. And it's information you acquire. We're not going to go through it, but basically there's wind speed, temperature, pressure, rate of change of pressure. The pilot works all this out because he needs it for actually to work out certain things with his aircraft. And we will look at that in a minute. So we're looking at my altimeter. Okay, we're looking at my altimeter. As I now say, I now need to make my altimeter work where I am. So now, where I am, okay, where I am, will have a pressure, okay? And on the instrument, you have what's called a pressure setting knob and a pressure setting scale, okay? The pressure setting scale sets the datum pressure for what the altimeter is going to work round, okay? It sets the pressure datum for what the altimeter is going to work round. So it says here the pressure setting scale will adjust dependent upon what letter code we're talking about. Okay. So there's my pressure setting scale. So let's have a think, gentlemen. Okay, let's have a little think. When does the pilot need to know his exact altitude? One of them will be when he's coming into land. So he needs to know how far he is above the airfield. Yep. So we need to have a datum that every single aircraft landing at that airport, its altimeter is set to. So we're going to set our aircraft to a pressure at the airfield. The next thing we need to look at is when the aircraft are flying about. Okay. Now, some of you boys are working on helicopters. Some of you boys will be working on smaller turboprop aircraft. Okay. So we actually have a level, okay, when we're flying around. So when we're flying around Kathmandu, the valleys, etc. That'll be controlled by the airport at Kathmandu. And it will set a regional pressure for the what they call flight information region round Kathmandu. So every aircraft below a certain height, doesn't matter where it is, because I know Kathmandu Valley is quite long, so the pressure will change between where at Kathmandu and as you go south, the pressure will change. If the aircraft just pick a pressure to start with, they could actually end up flying together and crashing into the air. So we're going to set a datum for every aircraft flying around at a low level, okay? And we call that below the transition height. And then we'll have a pressure setting for every aircraft flying high or what we call in controlled airspace. So there's 3 pressure settings we need to remember, okay? And they call them the Q codes, okay? The first one is query or QNE, query navigation en route. QFE, query field elevation. And the next one is QNH, okay? The 3 codes. QNE, QFE, and QNH. That's 3 specific pressure settings we're going to have, okay? I'll explain these a bit better in a minute. Right. Query navigation en route, okay? Query navigation en route. Let's look at every single aircraft flying going between countries. They fly high. Remember I showed you right at the beginning the pressure map? It was 1020 in New York and 1000 in Scotland. If I actually set the datum, if I only use the pressure from Scotland for one aircraft and the other aircraft, the pressure from New York, as we go around, theoretically, as the pressure across the Atlantic changes, one aircraft could rise, the other aircraft could fall. They're both indicating the exact same, they're indicating the height they were told to be at. So one might be told to fly at 31,000 feet. That's New York, high pressure. The one in Scotland sets off and it's got a lower pressure. And as they start to go, the high pressure to low pressure, this one is indicating in its altimeter 31,000 feet. It still indicates 31,000 feet. But because he's coming from a higher pressure to lower pressure, he'll start to come down. This one will start to come up. In theory, they could crash into each other, but both pilots think they are at the correct height because their altimeters were using two different pressure datums. Okay, two different pressure datums. So every aircraft flying above what's called the transition height sets the altimeter to 1013.25. Remember that figure again? Is the atmospheric model, standard atmospheric model pressure. But here I'm going to hear you say, Ian, at 30,000 feet, the pressure outside the aircraft is not 1013.25. And I would have to agree with you. Okay. But I'm going to tell you, for these aircraft, it doesn't matter. Two aircraft, again, Scotland, New York. They both take off high pressure, low pressure. This one here has been told to go to 31,000 feet. This one here has been told to go to 30,000 feet. But now, even if they go across the Atlantic, if they're all using 1013.25 as the datum, even if the pressure across the Atlantic changes, that 1,000 feet separation between the aircraft stays. So QNE, all you need to remember about QNE is the aircraft are set to 1013.25. So the altimeter is set to 1013.25. Okay, remember that. So all you need to remember about what is the pressure set in QNE is 1013.25, and we use it above what's called the transition height. Next one is query or QFE, query field elevation. And when I mean field elevation, I mean airfield. So basically, it's the pressure at the airfield. So now, when you take off or land, you contact air traffic control and you set the pressure, the atmospheric or the static pressure at the airfield. So now, when my altimeter is set to QFE, the pressure at the airfield, my altimeter should read 0. When I start to take off, it's giving me the height above the airfield. Okay, so QFE is the pressure at the airfield. Okay, so QFE is the pressure at the airfield. So we set the datum on my altimeter, the QFE, and that is the pressure at the airfield. Okay, it says the ambient or current static pressure at the airfield at that particular time, and it can change. Yeah, it can change. as the weather changes, the pressure will change. Even during the day, if it's cold in the morning, okay, and I know Kathmandu in the morning can be cold this time of year, but then come midday, it might be 20 degrees centigrade. That will cause the pressure to change. So throughout the day, QFE can change. It's a pressure at the airfield. Query navigation height, okay? Query navigation height, QNH. It's the height above the ground, or the pressure height above the ground where we are flying, okay? Up to what's called the transition height. That's approximately 5,000 feet above the ground, okay? It changes between country and country. It's 4,000 in the UK. I don't know what it is in Kathmandu. It's a regional pressure. So approximately 100 to 150 miles from Kathmandu airfield up to, let's say, 5,000 feet, the transition height, there is a set pressure for every aircraft to fly at. Again, it doesn't matter if I start over here with a high pressure and I start over there with a lower pressure. As soon as I get above the airfield, if I set the regional aircraft pressure setting, the QNH, as they fly towards each other, if they're told to be one at 4,000 feet, one at 5,000 feet, doesn't matter what the pressure change around the aircraft is, as long as they're using the same datum, any errors will be the exact same. So the aircraft will still have a separation. So when air traffic control told them go into QNH and they give you a height, all the aircraft are at the same pressure datum. Therefore, they shouldn't, he says, crash into each other. Okay. So it says there, it's a mean sea level pressure. We'll look at that in a second, but it's a regional pressure. Okay. It's a regional pressure. And we've actually calculated QNH already. Nope. There we go. So now, if I have a sea level pressure, and to be honest, for Kathmandu, it's going to be a theoretical one because you're quite a few thousand miles from the sea. But as you can see here, if I set a pressure, this formula doesn't change. So theoretically, using the standard atmospheric model, I can actually calculate my QFE using the QNH, okay? So that pressure there at sea level is the QNH, and I can theoretically calculate my QFE. Okay, so in your notes, gentlemen, you have to be able to understand the 3 Q codes. QNE is quite simple. It is basically the pressure set on your altimeter, 1013.25. It never changes. Yep. QFE, query field elevation, airfield pressure. It's the pressure at the airfield. So when I set the QFE on my altimeter, it gives me the height above the airfield. So in theory, when my wheel, if I set QFE as I start to approach the runway, and I'll get that from air traffic control, as soon as my wheels touch the ground, if my altimeter is set to QFE, it should, in theory, indicate an altitude of 0 feet. QNH is a regional pressure setting, okay? Roughly 100 to 150 miles round an airport, okay? And we use that up to what's called the transition height, which is approximately 5,000 feet. Anyone get any questions on the Q codes?
Excuse me, sir.
Yes.
Can you explain QNH once more?
QNH, yeah, okay. Let me go back to let's go for a new slide. Right. Now, as it says QNE, sorry, QN, oh, for goodness sake, I can't draw to save my life today. So QNH, that's a pressure taken from average mean sea level, yeah? It's a theoretical calculation, and the value is 30 feet equals 1 HPA, yep? So what we're going to do is, this is valid up to what's called, oops, the transition height. And again, that's about 5,000 feet, okay? I think you say 5,000 feet in our notes. So now, what happens? At the airport, we are set at QFE. So that tells me I've got my plane on the runway. If I set QFE, my altimeter will read 0. Yep. Now when I take off, if I have lots of aircraft flying below 5,000 feet, imagine that's Kathmandu and that's the other end of the Kathmandu Valley. It might be, let's say the QFE at Kathmandu is, at airfield level is, let's call it 1020. Down here, it's 1,000 hectopascals. Now, if I've got 2 aircraft, if they both take off and they both stay at that pressure, it could be to the point where if this one is told to go to, let's call 2,600 feet, this one is told to go to 2,000 feet, yeah. But now because we're going between higher and lower, we've got basically here, look, we have 600 feet. The difference of pressure is 20 HPA. And we now know that altitude will be 20 times 30 gives me 600 feet. So now this aircraft could climb, that aircraft could descend, they could basically crash into each other. So what we do is, okay, is Kathmandu is the regional air traffic controller, so we set QNH what's happened? So we set if I set my QNH to 1020, so now as soon as this aircraft takes off, it has to set its altimeter to 1020. This aircraft will have to set its altimeter to 1020. So now the datum for each altimeter is 1020. Even though that started there, as soon as it took off, it had to select QNH 1020. So now when they start to fly each other, that one has been told to stay at 2,000 feet, that one at 2,600, because they've now got the same datum, and it doesn't matter where they are, because it could meet, let's say, here. It could be meet here, and let's say it's 1010. Both aircraft will actually still have, they will both drop down by the same amount. So therefore, they're still going to have that 600 feet separation. So that regional pressure, every aircraft operating in that region, if they set the same datum pressure for their altimeter, when they start to meet, doesn't matter what pressure they took off from, when they meet at the same place, if they've been told to keep 600 feet apart, they will be 600 feet apart. Does that answer your question?
Yes, sir. But during flight, sir, during flight, if they have set the QNH pressure from both from different controller, then?
Right. No, because that's, we're saying this whole the Kathmandu Valley, let's say the Kathmandu Valley.
Yeah.
The pressure for that whole valley is set by Kathmandu Air Traffic Control.
Okay. During flight,
Okay.
when they will enter in Kathmandu Valley, they will ask with Kathmandu controller to.
What they do when an aircraft comes in, it asks the air traffic control for an airport information service.
Okay,
and one of the things they tell them is the QNH pressure.
Okay,
so as soon as an aircraft, let's say they've got an aircraft here, it's flying, and let's say it came from, let's say New Delhi. So it was flying from the pressure at New Delhi, and that was, let's say, 1030. As soon as he comes into Kathmandu air traffic control region, he asks for an air traffic control information service, and it will tell them that the QNH is 1020. So as he approaches, as soon as he crosses that, he will set his altimeter to 1020. The aircraft physically might go up and down a little bit because he was set at 1030, but now as he comes into that region, his height is set with every other aircraft in that region. It's using the exact same datum pressure.
Okay, thank you, sir. I got it. It, sir. Thank you.
Right, lovely. Thank you. Please ask questions. Okay, so please remember the 3 Q codes and what they mean. QNE 1013.25, anything above the transition height. QFE is the airfield static pressure, and just remember is if my aircraft is on the runway, ideally it should read 0 feet altitude. And QNH is a regional pressure, so all the aircraft under the transition, under 5,000 feet altitude, are all using the same datum pressure. Okay, all using the same datum pressure.
Hello, sir.
Yes.
So I got this. I understood this QNH and how it is used in altimeter.
Yes.
So and why QFE? At what situation this QFE is used in altimeter? QFE
Okay,
and
right.
QNE.
Okay, QFE.
Okay.
Okay, look at me last slide. Right, here's my airport. Yeah.
Okay.
And let's say QFE is 1,000 hectopascals. Yep.
Okay.
So now let's look at my aircraft. Okay. So at this moment he's below 5,000 feet, so he'll be set to QNH. Agree with that?
Yes.
Now when he gets in contact with tower, so he's now starting to land. Okay. Now the QNH for this area might be, let's call it 990. Okay.
Okay.
It's
okay.
a difference of 10 hectopascals. 10 times 30 equals 300 feet.
Mm.
So if it's 300 feet, it could mean when he gets to here, he's either 300 feet above the runway or 300 feet below the runway. Okay, that's bad. That one. This one, that's very bad.
Okay.
Okay, so now as he approaches, he will set his altimeter as he approaches the runway to 1,000. So now it's the exact same pressure here. So now when I set the datum pressure here, there'll be no difference when the aircraft touches down. So when the aircraft touches the runway, it should be reading 0 feet. If the aircraft starts to take off, it's telling him the height above the runway. Okay, because if he's got an emergency, he needs to know how far he's above the runway so he can. So the QFE tells him the actual height above the runway. Okay, QFE tells the pilot the height above the runway. So you can now see if the two pressures, the datum pressure and the altimeter, and the actual pressure at the runway itself, there is no pressure difference. Therefore, there is no altitude difference. So therefore, it'll be indicating 0 feet. Okay, does that make it? You happy with that?
But normally
Okay.
pilot will not set the QFE pressure.
Pardon?
Normally they will not set the QFE pressure. Just they will set the QNH only.
Yeah, yes, you're right. There's some airlines and pilots only flying QNH. Okay, you're correct.
Here Nepal, over
So
Nepal
what
also
happens
just
is
they will
now-
fly in QNH.
Okay, so what you
Yes,
need
sir.
to, if a pilot, this is a bit more, this is more advanced stuff, so you don't need to know it, but as the question's been asked, so I've now got QNH of 990. Okay, it's a lower pressure than this. So what I've actually got to do, again, I now have to make sure I know it's 30 feet. If it's lower pressure, that means I must be higher. Okay, agree with that? As we go up in altitude, the pressure goes down. Now, if I know the altitude of the airfield above sea level, so let's say the altitude is, oops. Come on, go back. If I know the altitude, okay, the pilots have to do a quick calculation. That calculation there. So if it's 300 feet, okay, above sea level, okay, I know my QNH. Therefore, I must land with my altimeter reading 300 feet. Okay, so pilots, when they actually land using QNH, will actually be reading at an altitude above sea level. So when you look at an aviation map, it'll give you the altitude above sea level for the runway. So what he'll be doing is, he will know, let's say, again, this one here, the altitude above sea level, that this runway is 2,000 feet above sea level. So when he's set to QNH, his wheels would touch the ground when his altimeter was reading 2,000 feet. Okay? But it's still a zero, if you understand, there's still a zero difference. Okay? Just be aware, but you still need to know the three pressure settings. Okay? QFE, QNH, and QNE.
Hello, sir. I got this QFE also. And
Yep.
In what case do we use QNE?
QNE is basically when I'm flying
Okay.
up high. Okay, so I'm flying above 5,000 feet.
Okay.
Okay, so now if I'm flying, okay, that was my transition height, that's 5,000 feet. Every aircraft above 5,000 feet, or the transition height, is QNE, and that's 1013.25 hectopascals. Okay, so everything above 5,000 feet of the transition height, every aircraft in the world sets 1013.25. Does that answer your question?
Yes.
Okay, lovely.
Thank you.
No problem. So QFE and QNH you get from the air traffic control. If a pilot does use QFE, and I can tell you, those who lot of helicopter work, they still use QFE a lot. Okay, when it lands down, because it's the pressure of the runway, your altimeter should read 0. Okay, and it said there the pressure setting of QNH will result in an instrument showing the height above an airfield above sea level. Okay, so that's QNH. So all you got to remember at QNH is up to the transition height, and it's measured from average mean sea level. Okay, and in case of Kathmandu, that's a theoretical calculation. Okay, because there's no, because how many thousand miles are you from the sea? Quite over 1,000 miles, I take it, easily. Yeah. So that's that. Right, before we go on to the next bit, what's up? Hello? Somebody's going to ask a question?
Around 1,338 meter.
Right, yeah, so it's a long way from the sea. So your QNH would be a theoretical calculation from somewhere. I don't know where the data would be taken from. Okay, so that's QNH, right? And we've been at it for about an hour. We'll go for a quick 10-minute break. Okay, come back in 10 minutes, and we'll go on with the next part. Okay, make sure you get up, stretch, have a drink.
Okay, sir.
Okay,
Okay.
10 minutes.
Okay. See you.
Lovely. Hello, we all back? Thank you. At least somebody's back. Thank you, Chris.
I'm back.
Lovely. Right, we all ready to make a start again?
Okay.
Okay, thank you. Right, so we've talked about QNH, okay? And it's that height from our average mean sea level, okay? Up to the transition height, which is 5,000 feet. QFE gives you the height above the runway, okay? So just remember that height above the runway. There's a whole load of different heights here. I'm not going to spend a lot of time in there, but you can see there's the transition height right in the bottom left. You can see QNH is above 5,000 feet, up to 5,000 feet. And then once we go above what's called the transition height or the transition altitude, we go to 1013.25. And again, that's the other place to get, that's where the pilots get their flight levels from. Right, there are a couple of little things we need to go through, okay? So that's the basic pressure settings for my altimeter, okay? The pilots have to use a couple of other pressures, okay? We'll have a quick talk about them. The first one, okay, what we talk about is elevation. That's the height above the land, above the sea level, okay? Call that elevation. So that's the definition. The next thing is a pressure or an altitude called true altitude, okay? True altitude. And true altitude, you have to set your altimeter to 1013.25, okay? Doesn't mean it is actually at 10, the aircraft is physically at 15,000 feet according to this. It just means that that altitude is true to every other aircraft, okay? As you can see here, it says there, the actual at 15,000 feet, there's the pressure, it's low. So therefore, that's the actual feet it would be physically at, but the altimeter is indicating 15,000 feet. So it doesn't matter, but every other aircraft is using that. So the atmosphere is true. Best way to think it is true to every other aircraft. The next one is called absolute altitude. Okay, absolute altitude is the altitude of the aircraft above the ground. Okay, some of you who are working on the rotary wing helicopters, it comes AGL, above ground level. Okay, so absolute altitude is the actual aircraft height above the ground. Okay, and if you look in your notes, there's a little formula for absolute altitude. It is absolute altitude equals QNH altitude minus elevation. Okay, so if I go back to this here, I'm indicating I am 15,000 feet. The ground is 2,000 feet. My altitude above the ground must be 13,000 feet. Okay, so please remember that little formula. Absolute altitude is QNH, and depending on the height, it could be QNE, but QNH minus elevation. Please remember that. Now, as you can see there, that's a bit inaccurate, but it doesn't matter when I'm up here, because every other aircraft is going to have the same error physically. But now when I'm starting to get low down, I need an accurate measurement of absolute altitude, or AGL, above ground level. And that comes in the form of not pitostatics, RADAL, the radio altimeter. The radio altimeter is the most accurate way to get a measurement of absolute altitude. Okay, so remember those two things about absolute altitude. The formula: absolute altitude equals QNH minus elevation. And the most accurate means of getting absolute altitude is RADALT. Yep. Okay, and that's the big thing about true altitude. Altimeter must be set to QNE. That's a whole load of information. The next thing is pressure altitude. Okay, pressure altitude. Again, it's the pressure, okay, of the aircraft. The pressure altitude, what the aircraft is actually indicating with my what the aircraft is physically at, with my altimeter set to QNE. Okay, so you can see here, there is what the aircraft is physically at, and this particular one, with 1013.25, is actually at 16,250 feet. Okay. That's all because of certain things. It takes into account QNE, okay? And we all know now, if I'm QNE is basically 1013.25. We know in the standard atmospheric model that the standard atmospheric model at sea level pressure was 1013.25. So I now know as I go higher, the pressure goes down. Therefore, it's going to indicate higher than I actually am. But also, if the average mean sea level pressure isn't 1013.25, that difference is also going to be felt up here. Okay, so all you got to remember is pressure altitude is the actual physical altitude the aircraft is at when the indicator, the altimeter, is set to QNE. Indicated altitude, okay? Gentlemen, when you get a component from the stores or the manufacturer, it doesn't matter what component it is, you always get a serviceability label, or in our case, a EASA Form 1. Is that correct? Yeah. With pitostatic instruments, you also get a second bit of paperwork. It's called a calibration sheet. And it allows you to take into, and the pilots to take into account any errors in the gauge. Okay, so that's why without this information, indicated altitude is basically what they call inaccurate or unadjusted. Okay, so how do I get it? I need to take into account my calibration. Okay, so calibrated in altitude is my altimeter, which is an indicated altimeter. But now, if I have my calibration sheet calibrating for the errors in the instrument, and something called pressure error. there is nothing we as maintenance engineers can do about pressure error. It has been reduced and taken into account by the designers of the aircraft. But calibrated altitude is adjusted for instrument error, for the calibration sheet, and pressure error, that's done by the manufacturer or the designer of the aircraft. And the last one, and it's probably one of the most important altitudes for pilots. Okay, it's called density altitude. Okay, density altitude. Basically, it's my pressure altitude, but now we take into account temperature and humidity. Okay, reason why we take pressure, temperature and humidity into account is we can't measure the density of the air in aircraft. You can measure it in universities. They're massive big machines. They're bigger than the size of the room I'm in now, sitting talking to you. So there's not a lot of room in aircraft. Now let's think about your engines, okay? To make your engines work, to provide thrust, I need fuel, I need air, oh, of course we need a spark, but let's consider the fuel and air. If I have let's say I'm at sea level, okay? I'm at sea level and my temperature is 15 degrees. I have a density of air. The air will be quite dense. If I start to go up, the pressure comes down and the density of the air reduces. So you can now see, if I have to make my engine run efficiently, especially when I'm starting and taking off at slower speeds, I need the fuel and I need quite dense air to get the maximum performance of my engine. So the higher my altitude, the less dense, the less efficient my engine is when I go for maximum thrust. Now, let's think about temperature. Okay, we now know if I heat air up, it expands and becomes less dense. So what density altitude is, it's basically using the standard atmospheric model. It talks about the density of the air going into my engine. So if I'm at sea level and it's 15, oh, what's going on? If I'm at sea level and it's 15 degrees and I have a density of, we'll call it a density of 1. If I go up, that density is going to start to go down below 1. Now, if I'm at sea level and at 15 degrees, I've got a density of 1, and I now start to increase the temperature at sea level, that air starts to expand. The air becomes less dense. So it's like me saying at 15 degrees, I have a density of 1 at sea level. I increase the temperature, the air becomes less dense. And as we now know, as I go up in altitude, also the air becomes less dense. So now if I increase the temperature for a same altitude, the air's less dense. So it's actually like my changing altitude. And that is what's quite important for pilots. They need the maximum amount of thrust available. So that's what density altitude. So what is density altitude? Okay, it gets the performance of the engines and it's taking the pressure and using the actual outside temperature and humidity to give me that density altitude. So what does density altitude depend on? is the temperature, so the actual pressure, taking into account temperature and humidity. Okay, taking into account pressure and humidity. Okay, that's a whole big thing there. Okay, we haven't got time to go through that, gentlemen, but just take that in there with what I've been saying. Right, so now we're going to look at temperature changes in the atmosphere, okay? And as it says there, the altimeter cannot detect changes in atmospheric temperature. But it says there, these changes will affect the atmospheric pressure. As we've now said, basically, as we have already said, if I change the temperature, the density of the air changes. Therefore, the pressure around the altimeter also changes, all because of temperature. Okay, so we're going to look at how that happens, and we're going to look at how we compensate for it in an altimeter. Okay, we will be looking at how we compensate it for it in a altimeter. But there's an important thing to remember. It says increasing temperature will show a drop in altitude. So if I come straight down, my temperature is going to increase. If I go straight up, my temperature is going to decrease, and it keeps decreasing until I get to the tropopause, or 36,000 feet, where it becomes a constant temperature of minus 56.5 degrees. Minus 56.5 degrees. Okay, so all happy so far on the basic altitudes, or the basic pressure settings and the pressure terminology they've got to use. Can you just tell me, has Sanjeev sent you an email yet with those question sheets? Zemin? Can somebody
Not
check
yet.
that? Pardon?
Not yet.
Okay, I'll remind them at lunchtime. If not, have you all got each other's email address? Hello?
Better
You can use Viber.
Okay.
better you send to our friend Yadav. He is our class coordinator, so he
What?
will forward everybody.
What, Yadav?
Yeah.
Yeah. Yadav, can you, at lunchtime, could you send me your email address?
Sure, I will.
Before lunchtime, I'll put my work's email address into the chat box, okay?
Okay, all right, copy it.
Right, lovely. So don't want to, because these questions will help you revise, gentlemen. Trust me, they will.
Okay, so then
Yes.
regarding this density and temperature relationship,
Yes.
that at the sea level, while the temperature increases, the density decreases, right?
That's correct. Yes.
But like while flying at a height from the ground level, so as the height increases, temperature decreases.
Yes, it does. Okay. But
so temperature and the density relation over here is just opposite as compared to at the sea level.
It is, yes. It's quite a call. We're talking about in a basic level. For the pilots, they really go into this a big, because it basically affects the performance of their engines. But this is the one, when the pilots are doing their calculations, depending where you are, okay, imagine here's a thing. Imagine I am at, let's say, Dubai. Okay, because quite a lot of aircraft go from Kathmandu to Dubai. Dubai is very near sea level. Well, let's say Dubai is at sea level. Yep.
Yeah.
Now, if I take off from Dubai, let's say it's winter and it's the middle of the night. Okay, you might find that the temperature, the outside temperature, we would like to say 15 degrees. So it matches the standard atmospheric model. Okay. So the density of the air is correct for the standard atmospheric model. Yep. And of course, remember I said all my aircraft instruments and all your engines, when we calibrate them and work them out, they work out to they're designed using the standard atmospheric model. So there's a set density, which we don't cover in here for the B1 course, but there's a set density of air, and that's for 15 degrees. Yep. And that's what your engine, the basic engine calculation for thrust is based upon. So now I'm at Dubai Airport again. I am now at summer. Okay. It's 30, let's say 35, we'll call it 35 degrees. We now know that the air is less dense at 35 degrees. So what I can actually say is it's like me starting and trying to take off from an altitude. Okay, so basically the air's less dense, so therefore when I'm using the maximum thrust, I don't have the same maximum thrust as I would when it was at 15 degrees. And that's one of the things the pilots do with the calculations, that they have to make sure that the amount of thrust they've got, they can take off, they can work out their V1, their V2, and if they can take off. If it's too heavy, because the engines, that's why sometimes when I've had to fly through Dubai, if I've arrived there in winter and at night time, they don't tend to weigh the hand baggage. If you arrive in Dubai in summer, they weigh all the hand baggage because the weight is no more critical because the temperature is higher. There is less dense air, therefore there's not enough, there's less available thrust to my engine. Okay, does that explain it a bit better to you?
Yes, Mr. Neil, got it.
Okay, lovely.
Thank you.
Right. So before lunch, we're going to start on the first instrument. And the first thing we're going to talk about is the altimeter. I remember what I said, the altimeter measures static pressure, the column of air. Okay, the column of air. Now, we'll just give a quick overview of the pitot-static system. This is a basic pitot-static system. There's no Mach meters or anything like that. There's two parts we look at. We've got the pitot and we have the static. Okay, the pitot is a mixture of static and dynamic. We'll look at this a bit more when we look at altimeter. But static is that column of air, the pressure caused by that column of air. And if you look at my three basic pitot-static instruments, airspeed, vertical speed, and altimeter, they all have static in common. But the only one that has pitot is the airspeed indicator. So we look at this other diagram, you can see it better here. Altimeter only has one static connection. So does the VSI, but the airspeed has two, pitot and static. Now, the first thing we tell you is every single one of these gauges is a differential pressure gauge. It's going to measure outside pressure to a reference. Okay, it's going to measure an outside pressure to a reference. So let's look at the makeup of what we call a simple sensitive altimeter. So this is what you're going to find in some of the little small, like Robinson helicopters, some of the little private, Cessnas and Pipers. Okay, does any small private aircraft work out of Kathmandu? The old single engine piston aircraft? Yep. No.
Yes, we
This
have
is-
Robinson.
You have some, yeah. This is the sort of altimeter you're going to get, okay? And to be honest, we got one for a test set back in Scotland about 2 years ago. To get one really, really good, simple, sensitive altimeter was about £400 to £500, UK pounds. We got a cheap one from China for 150. Okay. Officially, it still met all the requirements. Okay. I probably wouldn't actually fit this to a real aircraft, but people can. But let's look at the makeup of this simple sensitive altimeter. The first thing is the static port. Okay. That's usually on the side of the aircraft somewhere. Usually at the back, or it could be at the front. A lot of the Airbus and the Boeing 737s, the A320s, you just have a sort of silver metal, and you've got the little holes saying pilot, static, co-pilot, static. That's what we're talking about. And the first thing is the static only goes into the case of the instrument. The static only goes into the case of the instrument. So now when I go up and down, that static pressure will change in the case of the instrument. So if I go up, the static pressure in the case goes down. When I start to come down, the static pressure in the case goes up. So where do I get this differential pressure? It's all down to these aneroid wafers or aneroid capsules, okay? Remember I said aneroid means without air. So in my aneroid capsule, okay, the aneroid capsule has a vacuum. So no matter what the temperature is of the air, it's not going to affect the pressure inside the capsules because there's no pressure, it's a vacuum. So these are not the pressure, I'll use the word pressure, is not affected by temperature. We'll look at what is affected by temperature in a minute. So inside here, so we're going to look at the construction of the capsule first, okay? We're going to look at the construction of the capsule first. If you ever open up one of these, and you will have something similar in your aircraft. The only difference is you won't see the front dial, okay? You won't have this dial. It will be connected to some sort of electrical pick-off to give a pressure reading to give you a picture on your TV screen. But how it works is the basics of here. So let's think how it works. So we've got these capsules. We need to think about what these capsules are made of. And the first thing is they're made of a metal called beryllium copper, okay, or beryllium alloy. So remember that. What is the construction, or what is the capsules made of? They are made of beryllium copper, okay? Beryllium copper. Now, beryllium copper has some good properties that's going to help us measure differences in pressure, okay? So in your notes, I think you've got a bit that says capsule and the capsule makeup. It tells you beryllium copper is naturally springy. It can move, okay? It's naturally springy. It's ductile in nature. What that means is it can change shape, okay? Very similar to being springy. And the next thing, it says it's non-magnetic, okay? It's non-magnetic. So now, if I was asked to describe the construction of an aneroid capsule or an aneroid wafer, I will turn round and say it is made of beryllium. The capsule is made of beryllium copper, and inside there is a vacuum. Okay, and it's that vacuum gives me my pressure difference. So the first thing you need to remember is the construction of an aneroid capsule is made of beryllium copper with a vacuum inside. The next thing is, what is the properties of beryllium copper? It is naturally springy, it is ductile in nature, and is non-magnetic. Okay, you're required to understand and describe the construction of an aneroid capsule in a simple sensitive altimeter. You're also required to describe the properties of beryllium copper. Okay, you all can do that, can't you? Okay, good.
Yes.
Well, thank you. So let's have a quick look at what happens. As we now know, the pressure, this static port is in the outside of the aircraft. So whatever this static pressure is, that pressure outside the aircraft, that automatically goes straight into the case. And I said it was a differential pressure. So what happens now? Imagine now I am flying along in straight and level flight. So we have a set pressure in the case. What happens when I start to go up? Okay, so my altitude goes up, my pressure in the case is going to go down. Remember that? Inversely, opposite happens. I go up, altitude goes up. Pressure goes down. So as the aircraft goes up, the pressure in here starts to go down. Now look at these capsules. Inside there is a vacuum, okay? And the only thing it's holding the capsules in their shape is the pressure around them. So now, if the pressure around the capsule starting to go down, the capsules start to expand. That expansion is gone through some whole load of linkages, okay? So if that goes down, the capsule starts to expand. This rod starts to go down. This rod starts to turn. These sector gears also start to turn. And they're connected to the gears at the back of the instrument, and they control the pointers. As the pressure starts to go down, the gears are going to turn and it's going to indicate a climb. Yep. Come on. Right, so now let's look at if the aircraft starts to come down. So it's decreasing in altitude. That means the atmospheric pressure, the static pressure, is now starting to go up. So now the static pressure in the case is starting to go up. The pressure round the capsules is starting to go up. And that pressure now is forcing onto these aneroid capsules. Yep. Those aneroid capsules, as the pressure increases, because the datum is a vacuum, the capsules start to crush or start to get narrower. That movement, again, via all the linkages through the sector gears to the gears at the back of the instrument, will start to show a descent. Okay. So the first thing is to understand what happens when I go up and what happens when I go down. When I go down, the pressure inside the case starts to increase. If it starts to increase, the capsules start to collapse, crush, get narrower. And that movement moves the pointers. The next thing you have to understand, when I start to go up, the pressure inside the case starts to go down and the capsules will start to expand. Okay, and that again will give me the movement of the pointers. Okay, so you're all happy of the understanding of the relationship between the construction, beryllium copper, and inside's a vacuum. When I go up, the pressure inside the case goes down, the capsules crush, and that movement moves the pointer. When the aircraft starts to go up, the pressure inside the case goes down, less pressure, the capsules start to expand, and that movement, by through all the linkages and the gears, causes the pointer to move up and down. One other thing, remember I said it was a pressure differential gauge. Yep. If I had a leak or a crack in the case, would I have a pressure differential? No. If the seal between the front face and the case had gone, would I have a pressure differential? No. So if the aircraft started to climb, you had a leak, you're not going to get any pressure differential. Next thing to think about, if I have a crack or a leak in the capsule, as soon as the pressure changes, that pressure goes straight into the capsule. There is no pressure difference. Therefore, it will indicate 0. Okay, so be aware of that. If I have a crack or a leak in the aneroid capsule, there would be no pressure differential. Therefore, if the aircraft climbed or descent, the pressure in the case changes at the same time as the pressure in the capsule, and my altimeter will read 0. Okay, my altimeter would read 0. So please remember that. Okay, any cracks or in the capsules, there is no longer any pressure differential. And if the aircraft climbed or descended, the altimeter would always read 0. Okay, in a basic, simple sensitive altimeter, there is 3 pointers. Okay, there's the first one, and it's usually the big long one. That's the 100-foot pointer. Okay, and one complete revolution, it starts at 0, goes all the way around, back to 0. The next pointer will move. That's the 1,000-foot pointer, and you can see there it's a smaller one. It goes all the way around, so it basically goes from 1,000 feet all the way around, 9,000 comes to here, becomes 10,000 feet. After that, the 10,000-foot pointer will move 1. So we've got 3 pointers. It takes one complete revolution of one pointer to move one segment of the next pointer. So what I can say is the relationship between the pointers, or the gear relationship between the pointers, must mean it is a relationship of 10 to 1. So one complete revolution of the 100-foot pointer, so 10 lots of 100 gives me one movement of the 1,000. Remember that the relationship is 10 to 1, not 1 to 10. So I need 10 movements. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 back to 0. And then the 1,000-foot pointer will move to the 1. Okay, so the relationship between the pointers is a gear relationship of 10 to 1. Okay, the next thing here is this crosshatch flag. Okay, this crosshatch flag. When it's there, when you can see the flag, it indicates that the aircraft is below 10,000 feet altitude. Okay, 10,000 feet altitude. That's above sea level. If it goes above 10,000 feet, a little black shutter is pushed across that flag because you don't see it. Why is that there? Okay, if any of you have seen any YouTube films or films about decompression of the aircraft, you'll realise if you get a rapid decompression, you get a fog. There might be bits of paper or maps flying around in the cockpit. It can be quite difficult to see the gauges. And one of the things that happens is if the pilots get a rapid decompression, they have to descend below 10,000 feet to get breathable air. And if you've got that fog or this disorientation, you can't see it. When the pilot sees that crosshatch flag, he knows that the aircraft has descended below 10,000 feet and we can come off oxygen. Okay. So just to highlight the basics of, before we go for lunch or go for a meal, lunch in my case, I think it's what, it must be 6 o'clock your place. Construction of a simple altimeter. Static to the case only. Inside you have aneroid capsules, okay, and you have 3 of them. We have 3 of them to increase the sensitivity because we're only talking about tiny movements of the capsule. So we can multiply it by 3 times, okay? So we have 3 capsules to increase the sensitivity of my aneroid capsules. My aneroid capsules are made of beryllium copper, and inside them is a vacuum. Beryllium copper has 3 big properties we need. It's naturally springy, it's ductile in nature, and it's not magnetic. If the aircraft climbs in altitude, the pressure inside the case increases, the capsules will crush or narrow, and that movement is made to the pointer. If the aircraft descends, so the aircraft goes up, the pressure inside the capsule goes down, the capsules will expand. The pointers, there's 3 of them, a 100-foot pointer, a 1,000-foot pointer, and a 10,000-foot pointer. They have a ratio of gearing of 10 to 1. What is the purpose of the crosshatch flag? It's there to indicate the pilot when the aircraft is below 10,000 feet above sea level. And one other thing, and I keep saying it is a pressure, an altimeter is a differential pressure gauge. If the capsule was to split, okay, it doesn't matter if the aircraft goes up or descends, the pressure will change in the case and it will instantly change in the capsule. We no longer have any pressure difference. We have 0 pressure difference. Therefore, my altimeter will read 0. Okay. Are we all happy on the basic construction and operation of an altimeter?
Mr. Lin,
Yes.
This last condition of crack or rupture or something leak
Yep.
is the same as the static port is when it is blocked, right?
No. No.
What
No.
will read when the
A
static
we
port is
don't
blocked?
go to that depth in here, but if this static port was blocked, yep, and it was in the altimeter was reading, let's call it 5,600 feet. Yep. If the static port was blocked, whether it was ice or something hit it, is the pressure in the case changing? Hello?
No.
No. So now, if the aircraft climbs, we know outside the pressure is going to go down.
Yeah.
Yep. But because the static port is blocked, the pressure inside the case doesn't change. Yep.
Okay.
So if the static port ever gets blocked and the aircraft climbs or descends, the altitude stays the same. Yep.
Okay.
But in this case, if I'll just draw a capsule. Okay, and we said in here's a vacuum. Yeah, and that's connected to a rod, and that's connected to my pointer. If the aircraft starts to descend, the pressure acting on the capsule causes it to crush. Agree with that? Yes? Who's asking the question? Okay, so that's my differential pressure. The pressure in the case, if I now put a hole or a crack in that, the vacuum has gone. So the pressure in the case is the exact same now as the pressure in the capsule. There is no pressure difference, therefore there is no movement. Therefore, this will indicate the altimeter will read 0. Okay, does that answer your question? Hello?
Yes.
Okay. Right. That's lunchtime, or in your time. I think it's 6 p.m. in Kathmandu now.
Yes. 6:02.
Okay. So you'll be going for dinner, and I'll be going for lunch.
Okay.
So we'll be back in an hour. Okay. Back in 1 hour.
Okay.
Okay.
Okay. See you.
Okay. I will see you then.
Okay.
Ayan,
Yes.
please
Yes.
get my email from the chat room, okay?
Okay. I'll look at that. Yes. If you send it in the chat room, I'll pick it up now.
Okay.
Got it. Okay.
All right.
I'm going to send the email right now. So it'll be a couple of minutes, and it should be there.
Okay. Yeah, thank you. I have got the email.
Okay. Right, I'll see you after
Okay.
lunch
See you.
or dinner. Good afternoon, gentlemen.
Afternoon.
Good. Did you have a big lunch? Big dinner, sorry? Are you having that later?
Have later.
All right.
Mr. Lin,
Yes.
is it okay if we call you Mr. Lin?
Hey, just call me Ian. Just call me Ian. Don't need sir, don't need mister. Just call me Ian.
Okay. Okay, thank you.
Okay, I'm no different from you. I was an aircraft engineer, so
It's okay.
boss, I'm just the same as you, so just call me Ian. Okay?
Thank you. Thank you. Okay.
My name. Okay. Bet I can see again.
Thank you, Ian. We got the questions.
Good. Okay. They will help. Okay, we'll talk about them later on.
Okay.
Okay, then actually, I got disconnected before the lunch regarding that. I asked you one question that static port block. I understand that. After that, I think you said one other point. I can't get
It'd
that.
be static. Okay, if I said is a
Yeah.
static, if you look at the view I've got here on the PowerPoint, if the static port is blocked, there's no change in pressure in the case. Okay, so now if the aircraft starts to climb, there can't be any change inside the case. So the pressure inside the case stays the same. So no matter what the outside pressure, whether it goes up or down, inside the case is the same. And if the pressure inside the case is the same, the altitude is frozen. Okay? The altitude is frozen. Okay, it doesn't move. Okay, but we don't go that in depth in this course. This is the basic course. Who was it asked the question?
Yes, yes, thank you.
Who's that? Tia. Who's Tia? Is the virus bad in Kathmandu?
Pardon, Ian?
Is the virus bad in Kathmandu?
Not so bad.
Oh, good. It's quite bad here.
Mhm.
You having to walk around wearing masks?
Yes, we can walk around, but we have to wear masks.
Yeah. Same here. Same here.
They're okay, Lin? Is it still lockdown there?
And we're still in lockdown, yeah. Yeah, that's why we're not even allowed to leave the country. In fact, we're not allowed to leave our county. So we can't really move about at the moment. I'm stuck in me house. Okay, that's my only time out is to go and make sure my elderly mother's okay.
Okay. So are you vaccinated or still
No,
not?
not yet. No, it's just the.
Okay.
It's only the elderly have been, the over sort of 75s that have been vaccinated. But they reckon next month, maybe 2 months, hopefully I'll get mine. Hopefully I'll get my vaccine.
Okay.
So I wouldn't mind coming back out to Kathmandu and do some of this teaching. It's a lot easier to do for me and for you if you're actually out there. As you can probably notice, I'm someone that likes to use my hands. Okay, we all here? Who's missing? Harim. There was 19, there's another 4 to come in. Okay, give him a minute. We did say what? We did say an hour.
Mr. In,
Yes.
you can leave those link in chat room so we can go through it.
Yeah, I know. Yeah, I'm just trying to copy it so you can have a look at it later. Once I get my pointer. Didn't we do that? Oh, didn't we do that either? Right. That's not an important one anyway. Okay, we're all here. We're all ready to go. There are a few people still waiting, but
Yeah. After that, may I ask you one question last?
yes, you can.
Then this crosshatch flag is if the aircraft is below 10,000 feet
You see the
above
cross. You see
level,
the crosshatch. Yes.
crosshatch. It means what is what indicate its crosshatch? This only this 10,000 above the sea level.
Yeah, it basically tells you when the aircraft is 10,000 feet above sea level. Okay, sorry, it appears when it's below 10,000 feet below sea level. When you go above 10,000, there's a shutter comes across and hides it. Okay, so when you're above 10,000 feet, you don't see that crosshatch, that black and white. Okay, so if the aircraft has to descend, like rapid decompression, you have poor visibility in the cockpit, might have difficulty seeing needles. That crosshatch, and it is quite big in the bottom of the gauge. You can see that, then the pilot knows he can come off oxygen, he can level out, etc. Then do the rest of the stuff he does to get, because the passengers hopefully can breathe in the back of the aircraft. Okay, does that answer your question?
Okay, thank you.
Okay, no problem. Right. Now, what do you think? We think about now. We talk about next thing we're going to look at on a basic altimeter is temperature compensation. Okay. Temperature compensation. In this particular case, we're not specifically talking about temperature of the atmosphere, okay, or the gases, but the temperature of those gases is going to affect this metal, okay? The beryllium copper capsules, they're quite thin, okay? Quite thin. And as we all know, temperature affects metals. The colder the temperature, the stiffer a metal can be. So imagine you've got a sheet of metal. It gets very cold, it becomes stiff. And if it becomes very hot, it becomes quite flexible. And it's the exact same with these capsules here. Okay, with these capsules here. So let's give a little scenario. I'm flying along, okay, I'm flying along at the exact same height. Okay, I'm flying along, let's say 5,000 feet. It starts to get colder, okay? It starts to get colder. Now these capsules become stiffer. Okay, these capsules become more stiff. So let's now, remember I said all these pressures in the case, we're talking very, very, very small pressure differences. So now when it gets cold, these capsules become stiffer. So now when I start to climb or descend, okay, let's say when I climb or descend, because they've got stiffer, they're not as sensitive, okay? So these capsules, because it's got colder, are not as sensitive. Let's say I stay at the exact same height, and now it gets warmer. The beryllium alloy capsules get hotter. The metal becomes softer. So now the changes in pressure actually affect it more because the metal's softer. So what we have to do artificially is make sure that our capsules move the same amount for a particular change in pressure, regardless of what temperature it is outside the aircraft. So we're going to look at something called temperature compensation of a basic sensitive altimeter. And there's two parts to it. The first bit is a bimetallic U-spring, okay? A bimetallic U-spring. Bimetallic is two metals, okay? Two different metals. And the two different metals, when we heat them up or cool them down, they expand and contract at different rates. So if I was to say, oops, if I was to say, oh, where's my pen gone? I have two metals. And at 15 degrees, both are straight. Okay, both at straight. Now let's make it 0 degrees. Okay, the metals will bend or expand at different rates. So this one here will expand less than the one on the right. And what would happen is the metals would go like this. If I said 30 degrees, the metals would go like that. Okay, so that's the bimetallic U-spring. Oh. That's the bimetallic U-spring. Right, so let's have a look at this here. So the bimetallic U-spring, that's going to bend either inwards or outwards, depending on whether the temperature increases or decreases. So that's the first part of the temperature compensation. The second part is this thing called an inverse steel. Okay, inverse steel pin. Going to tell you a little bit inverse steel. Inverse steel is a it's an alloy of steel. Okay, it's an alloy of steel. But this invar steel has one property that we're going to use for temperature compensation. Over a wide temperature range, and I think it's like -65 up to plus 50, 56, 57 degrees centigrade, the metal does not expand or does not contract. Okay, so invar steel has a constant length no matter the temperature that we are going to use it in. Okay, so the length of an invar steel pin doesn't change with temperature. We're now going to put both them together. And if you look on here, okay, there's my bimetallic U-spring. There's my invar steel pin. And this length here and here is fixed. That doesn't change. Okay, so remember that the invar steel, the length of the invar steel pin doesn't change length. It's a fixed length. Now, let's have a think about metals again. When a metal gets hot, it becomes softer. So any small changes in pressure will get a bigger movement on the capsule. So we artificially have to make the capsule stiffer. So what happens here? Okay, what happens? At 15 degrees, the sides of the U-spring the bimetallic U-spring are straight. And any change up and down goes straight to the pointers, which moves straight to the ranging bars, which moves the pointer. Now it gets hotter. So let's say now it's getting to 30 degrees centigrade. Okay, we're going to raise the temperature to 30 degrees centigrade. These capsules here become softer because they're hotter. So what happens is the invar steel pin, so the bimetallic U-spring bends inwards. Okay, the invar steel pins push down onto the capsules, artificially making them a bit more stiff, bit harder. Let's now look at the temperature when it goes down to 0 degrees centigrade. And we now know that metals, when they get colder, become stiffer, harder. So what happens now for temperature compensation? The bimetallic U-spring bends outwards. The invar steel pins pull the capsules slightly apart, making them artificially softer. Okay, artificially softer. Now, you're not going to be asked to describe how the bimetallic spring moves. Okay, all you got to understand is it bends in and out at any temperature greater than 15 degrees. So at 15 degrees, the sides of the bimetallic U-spring are straight. As the temperature changes, the sides will move. You don't have to remember which way it bends in or out. I'm just showing you there. Okay, and as the invar steel pin is a fixed length, that will either pull or push the capsules in or out. So what have we got to take out of this so far? Is temperature compensation on my simple sensitive altimeter. We use a bimetallic U-spring and an invar steel pin. Invar steel pin is a steel alloy that doesn't change its length with increase or decrease of temperature. And remember how I always said right at the beginning, all our instruments are calibrated according to the standard atmosphere. So the temperature, so when this doesn't have any temperature compensation, it's when the sides of the U-spring are straight at 15 degrees, okay? So one of the sides of the U-spring straight, it will be at 15 degrees centigrade, okay? Will be at 15 degrees centigrade. We're going to look at adjusting the altimeter. So we're actually, you can look at that video there, you can see he's adjusting the pressure setting scale. And as we move the pressure setting scale, you can see it there, it's changing the pointer, the height, okay? And what he's doing is setting the datum, okay? What he's setting the datum pressure for my altimeter. Let's show you that again. So adjusting the pressure setting knob, you can see here it's setting the pressure setting window, okay? Now, if you actually look at that bit, imagine that now was the aircraft on the ground. It's reading 0 feet. The pressure in the pressure setting window would actually be the pressure at the airfield. And the pressure at the airfield is known as QFE. Okay, so you can see here, there's the pressure setting knob. That's your pressure setting knob. All you're going to do is adjust the datum pressure, okay? And that will move the windows, okay? That will move the windows. Now, one last thing, okay? And I keep saying, remember the pilots are supposed to be in the top 10% of the intelligent people in the world. And they came to the manufacturers of aircraft and aircraft instrumentation and said, trying to work out the height with 3 needles is difficult, okay? So they came up with this, it's only 1 pointer. And in here, you've actually got numbers, okay? So the main numbers, so that would be like 30,000, 100, 200, 300, 400, 500, 600, 700, 800, 900, back to 0 again. That's one more advanced altimeter, okay? If a pilot can't count 3 gauges, he shouldn't really be a pilot. I wouldn't trust him to fly me. You can see better there, there's that little crosshatch flag. And the last thing here is that bit it says encoding. Okay, encoding means it can send out an electrical signal reference to the height of the aircraft. So an encoded altimeter can also give height and an electrical output reference to the aircraft's height. Okay, and we'll look at that in a minute, because a lot of aircraft now you need to have the actual height we'll send to your transponder, and we'll look at that a bit more in depth when we look at the avionics module, because you've all seen it. You've got the squawk code, the aircraft reference number, and the aircraft's height, and we'll look at that in we'll look at avionic module. Okay, now, oops, my simple sensitive altimeter. Okay, my simple sensitive altimeter relies on small pressure changes. Yep. And it also relies on small pressure changes moving mechanical linkages. So a simple sensitive altimeter isn't as accurate as it can be because of any changes in the gear. If the capsules become stiffer, the gears become stiffer. And they're not very good at low level. Okay. Now, to be honest, gentlemen, most 737s don't do 500 knots at 200 feet. That's usually military aircraft. But things like helicopters flying low, fast, some of the maybe the sort of like the sports player, the pit specials doing the flying. Okay, but also think about it. When you take off, the aircraft is flying 200 to 300 miles an hour, so what, nearly 300 kilometers an hour, and it's climbing away 50, 70, 100 feet. And if my altimeter wasn't responding to that change of altitude fast, if the pilot has an emergency and needs to see and do something and he needs his height to make a decision, if my altimeter was maybe a second and a half behind in a pressure change, you can see it might be several hundred feet behind at the speeds that these aircraft are doing. So for small private aircraft, small helicopters, it's not a problem. But in commercial and faster aircraft, this what we call instrument lag, okay, isn't good. Okay, so we need to do something to make my simple sensitive altimeter not have instrument lag. And what we're going to do is use something called a servo assisted altimeter. So a servo assisted altimeter gets rid of instrument lag. It's now accurate at low levels. It can change, it can display large changes in altitude with very little time lag. Okay. And as I also said there, if it's got an encoder, I can provide information to my SSR, my transponder. It can give me an electronic output of height. Okay. That's what we talk about now, is a servo assisted altimeter. And its prime thing is to get rid of instrument lag. So let's look at the principle of operation. Okay, we're going to look at something called an E and I bar transducer. Okay, an E and I bar transducer. So how does this thing work? Okay, if you can remember back to module 3, gentlemen, you've all done module 3, have you all done basic electrics before?
Yes, Mr. Ian, we have did it.
Oh, good, lovely. That makes life a lot easier for me. So we now know, back to that magnetic fields like to go through metals. Magnetic fields don't like to go through air. So in this particular one, I have, there's my capsule, the bronze or the brown colour, that's my capsule. That's going to change with pressure. It's connected to an I bar, and you can see here the I bar, its pivot is off centre to where it's getting forced. So basically, it is its pivot point, and there's its centre. So what we're going to do now is I'm going to put an AC supply round the centre leg of the E bar. We're going to put an AC supply. So an AC is going to go back and forward. It's going to create a magnetic field flowing in one direction than a magnetic field flowing in the other direction. Okay. Cool. Right. So what I'm going to do now is I'm now going to put a coil of wire on each of the legs. Okay. In each of the legs. So now it's going to produce a magnetic field. Okay. So I'm putting an AC waveform here, and it's going to produce a magnetic field in that dotted line. And let's, for instance, just say that the magnetic field and the top leg flows in the clockwise direction, and the magnetic field, the magnetic field in the bottom leg flows in the anti-clockwise direction. And if I have an AC waveform going back and forward through a coil of wire, it's going to induce a voltage. Yeah, going to produce an AC voltage. Now, I'm just going to draw these lines further out. Okay. And I'm going to put it to a little amplifier. Positive, negative. Okay. I'm just going to say right now, at this instant in time, as the leg, okay, as the AC and as the AC comes in here, it's back and forward. Remember the word reluctance? Reluctance is the ability or the ability to pass a magnetic field. Well, there's very, very low reluctance in the leg. There's a high reluctance here, okay? But the overall resistance to the magnetic field when the I bar is central, so we've got an equal gap between the legs of the E bar and the I bar, the voltage produced in each leg is the same. So let's say I'm going to produce 5 volts here and 5 volts there. So now I'm going to have 5 volts going into my little amplifier. I have a +5, a -5, so therefore coming out of it is 0. Yep. Just for this instant in time. So it's flying along straight and level. That's what it does. So now aircraft now starts to climb. The pressure outside the capsule starts to decrease. Okay. And it pushes that rod. And you can see now the rod, because it's pivoted off center, the top part moves towards the top of the E bar, and the bottom leg moves away. The bottom leg moves away from the bottom of the E bar. So what we can now say is the reluctance of the gaps here has become it's not moving. One. The reluctance in the gap here has become low. The reluctance in the bottom leg has now become very high. So now we can actually say there's more resistance to the magnetic field. Therefore, the voltage in the bottom leg has gone down. And let's call that 2 volts. Up here, the reluctance or the resistance to the magnetic field has gone down. So its output voltage is going to go up. And let's now call that, oops, 8 volts. So now I have 8 here, 2 there. I've now got an output Okay, so that's minus 8, so that's 8, and so basically now I've got an output of 6. And that voltage, whether it's positive or negative, will determine whether it's going up or down. The aircraft's going up and down. Okay, so in a servo-assisted altimeter, the principle of operation is an E in I bar. As the capsule moves in and out, it changes the reluctance gaps between the I bar and the E bar, and that will change the voltage induced into the coils, and that will produce a voltage. Okay, a voltage. I've described it as an instant of time, or equivalent to a DC. Okay. We have to talk about it as an AC system. Okay. So the direction, there's me. The direction equals the phase change, whether it becomes anti-phase or positive, or anti-phase or in phase. Okay, determined by the phase. Okay, phase of the AC. The rate of change is determined by the voltage produced. Okay, so the bigger the voltage, the bigger the rate of change. Okay, so far we need to think about a couple of things. In a servo-assisted altimeter, what is the principle of operation? It's an E and I bar, and it's the reluctance. Oops. It's the reluctance between the I bar and the E bar. When we change height, that reluctance changes, and it changes the output voltage. That's the principle of operation. Now we've got to understand what information it gives us. So whether the two voltages are in phase or out of phase will determine the direction whether the aircraft is going up or going down. How fast the aircraft is going up is the voltage produced. Okay, is the voltage produced. So remember those three things: the principle of operation, E and I bar, reluctance change. Next thing you have to remember, what determines the direction? The direction is determined whether the voltage produced is either in phase or out of phase, and the rate of change of height is determined by the output voltage. Okay, output voltage. Are we all happy with that, ladies and gentlemen? Yep. Anyone get any questions on it?
Not at all.
Okay, good. So that's the basic principle. Let's look at how it works in theory. Here are my capsules. Okay. Let's say the aircraft now starts to climb. The I bar moves. The reluctance changes. I get an output. Okay. That output is fed to the amplifier and it's amplified. The voltage now comes to the motor. The phase between the two outputs will determine the direction of rotation of the motor, and the voltage will determine how fast the motor rotates. Motor out through the gears, starts to move the pointer. Okay, starts to move the pointer. If I don't do anything else, that output will just keep going and going to the base of the machine. The counter explodes. So I now have to do positional feedback. I need to stop it. So now, as the aircraft climbs, the gears turn, the pointers turn, and that pointer now works on to this gear, which is connected to what's called a worm shaft. It's connected to another big gear cog, and that moves that cam, which moves the cam follower, which moves the E-bar back to a datum position, a datum gap between the two legs. But as long as the aircraft is climbing, that I-bar will constantly change. So the gap will either, the gap between the two legs will be different. And that gap will stay the same until the aircraft stops climbing. And as soon as it stops climbing, the I-bar stops moving. There is still a gap, a change in the gap between the E-bar, the top of the E-bar and the bottom of the E-bar. That output will go to the amplifier, goes to the motor, turns the pointer, moves the gear, which moves the cam, which puts the E-bar back into its datum position. And as soon as it's back in the datum position, the reluctance gap between the E and the I-bar is the same. Nothing comes out the amplifier. And this works literally in fractions of a second. Okay, in fractions of a second. So what we've talked about is, how do we get an output? There's a reluctance gap between the E and I bar. Goes to an amplifier. The phase of the voltage will determine whether it goes up or down, and the amount of voltage will determine how fast the motor goes. And the pointers of the servo-assisted altimeter will keep going until the aircraft stops climbing and the E-bar is driven back to the datum position. Okay, so when the aircraft stops moving, it's the E-bar, it moves back to the datum reluctance gap. Let's look at setting the pressure setting scale, or the pressure setting knob. This time I change it. Now look what happens. I change it. I move this millibar adjustment rod, which moves this M lever. Okay, basically I push that way, that moves that way, that moves this cog, which moves the cam, which moves the cam follower, which moves the E-bar. And if the E-bar moves, the reluctance gaps changes, we get an output. Okay, so when I move the pressure setting knob, ultimately, what am I moving? I'm moving the E-bar to give an output. Okay, so remember that, gentlemen, when the pressure setting knob is moved on the servo-assisted altimeter, it is the E-bar that is moved. Okay, you happy in that basic understanding? Yep. Anyone get any questions on that? No, good. Okay, let's look at a safety device. Now, from my point of view, I'm an electrician. And I will say the electrics are the most important thing in the aircraft. And of course, you B1s will say, no, they're not. And of course, as we all know, you're wrong. Except in the case of a servo-assisted altimeter. One of these servo-assisted altimeters like to put into, like, say, a little private aircraft or a business jet. A basic one costs about 40,000 UK pounds. Okay, 40,000 UK pounds. It's nothing to do with the little bits of wire or the amplifier of the motor. At most, that might be several hundred, maybe £1,000. So all the wires, the transistors, the motor is less than £1,000. What makes it more expensive is the gears And all the mechanical aspects in there are very, very highly machined. So the tolerances in this servo-assisted altimeter for the gears is very, very, very small. So we don't want to damage it if the electrics go long. So we have a safety device. And this safety device is called an overrun switch. And what happens here, imagine now the solder connection or one of these wires going to the amplifier breaks. I'd have 5 volts going into the amplifier, nothing going into there. 5 volts, the motor will start to turn. Okay, start to turn, the pointers will start to turn. The cog will start to turn, the cam will start to turn, the cam follower and the E-bar will start to turn. But it doesn't matter what happens because I'm always going to have a voltage here and nothing there. So what will happen is the pointer will keep going round and round and round till it explodes. That's 40,000 UK pounds gone. So what we have is something called an overrun switch. And it's only one, but we'd actually have 2 of these. One at one end of travel, on that one gear, and the other on this end. And if you look here, when the overrun switch, the cam hits that, it breaks that electrical contact. And that electrical contact will be like a switch there. Okay, so normally this switch is in the closed position, but when the overrun switch hits it, it brings it out, removing the supply from the center coil, no AC magnetic field, no back and forward magnetic field, nothing changes, no output, okay? So what is the safety device in a servo-assisted altimeter? It is the overrun switch, okay? It removes the power supply. So, things to highlight on this. We know now how it works. The capsules move, the I-bar moves. Output to the amplifier. The motor, its direction is determined by the phase of the voltage, the AC voltage, and its speed is determined by the magnitude or the size of the voltage. The pointer will stop when the aircrafts come to rest and the E-bar is driven back to the datum reluctance position. When I move the pressure setting knob, I ultimately move the E-bar, the reluctance changes, I get an output, and again that will move the pointers. I have a safety device, and that safety device is an overrun switch that when mechanically it reaches its end of travel, that switch open, removing the supply to the E-bar. Okay, you happy with those basic description of the servo assisted altimeter? Okay.
Yes, Lynn,
Yes.
this safety device, this overrun switch, how
Yep.
does it sense? How does it sense so that it opens itself?
So what happens is, okay, if this motor keeps turning and turning, agree with that? So the motor keeps turning, the pointers will keep turning, this gear will keep turning, this worm shaft will keep turning, which will cause this cam to move. And what will happen when it gets to, just before it gets to the end of the mechanical, as far as it can go, before it hits the end stop, if it was to hit the end stop mechanically, and I don't remove the electrical supply, the motor would still want to keep turning because I'm getting an output from the E-bar. Agree with that?
Yes, Lynn.
Right. So what happens here is to avoid all the mechanical gears and linkages getting damaged, as soon as the cam hits this switch opens, removing the supply to the center coil in the E-bar. Therefore, I have no longer got an AC going back and forward, which means I don't have anything going into the amplifier, and the motor stops turning. So it's a safety device at the end of the travel, mechanically at the end of the travel of the cog, which removes the electrical supply. So the electric might have to replace some wires when I take it back to the workshop, but mechanically I haven't damaged any of the cogs. Does that answer your question?
Yes, so it's during the without supplying, when we apply the knob fully, it protects at that time.
Yeah, so basically, if I get to, let's say that the pointer, its maximum height is 60,000 feet. Okay, so by the time the cam gets to 60,000 feet, it's actually mechanically at the end of the gears. Okay, the gears can't turn anymore. If I still had an output, mechanically, this can't move anymore. Yeah. But if I had an output from the E-bar, the amplifier, the motor would still try to turn. The gears couldn't turn because mechanically, they're all connected to that one gear shaft. If that one gear shaft can't turn, if the cam or the cog on the cam can't move. So the motor would end up burning out, and also the cogs, the gears, the splines in the gears would be damaged. So when this gets to the end of the travel, it opens that switch, electrically removing the supply to the E-bar.
Okay, thank you.
Okay, no problem. Now, one last thing on this. As another name for this is called, oops. Oh. It's called a barometer. The other name, the posh name, is a variometer. So you sometimes might hear it called a barometer, or, oh, come on.
Instantaneous.
Yeah, a variometer, okay? Now, one last thing, okay, we'll talk about on this diagram. Have you ever heard the phrase hangar pilot? Somebody goes and plays with the aircraft in the hangar. Okay, we don't have any power on the aircraft. Okay, we don't have any power on the aircraft. And someone comes in and turns the millibar pressure setting. There is no power on the aircraft, but mechanically, I can move eventually the E-bar. Yep, but there's no power on the aircraft. Therefore, I've got no output. Nothing happens. Let's say now I move this 1 millibar. Yeah. Move the pressure setting scale with the power off 1 millibar. 1 millibar equals how many feet? It equals, sorry, 1 hectopascals equals 30 feet.
Yes.
So now I move this by 1 hectopascal. I switch the power on. I have an error of 30 feet. And my pointer will go deep. It will move slightly. Yeah. Imagine now I move it a 100 hectopascals. It's going to move 3,000 feet. Yep. So let's now say I've got the power off the aircraft. I move the pressure setting knob. I move the E-bar. I now put power on. I have a big gap. I've got a big error. The voltage out there is going to be big, and it's instantaneously going to be big. The motor, the shock or the torque caused by the motor can damage the gears. And remember how I said the gears are the cogs and the gears are the most expensive thing about this. So we don't want to damage this mechanically. So there's a warning. You'll find this in the maintenance manual at the chapter beginning, anything to do with pitostatics. It will say the pressure setting knob of the servo-assisted altimeter must not be operated without electrical power to the instrument. Okay, that's a warning. So basically, you must never ever adjust that pressure setting knob without the aircraft power being on. Okay, it's highlighted nice big red letters for obvious reasons. One, you don't want to do it for real in the aircraft, and there's another reason it's in red. You can work that one out, ladies and gents.
Len,
Yes.
this overrun switch does not function at this condition?
Only if it were to go to the end of the travel. Okay, it would only go if it went from 0 feet to 3,000 feet, it's not going to hit the overrun switch. Agree with that?
Okay.
Well, we're talking going from 0 feet to 3,000 feet instantly. So the torque on the motor will be big. So the possible damage to the gears and the cogs is going to be big. Yep.
Okay, thank
Right.
you.
Okay, no problem. Next one is we're going to talk about, it's called a cabin altimeter. A cabin altimeter, most of you, if you're working on the Airbus 320s or the 737s, 800s or whatever, you probably won't see one of these nowadays. But in some of the older aircraft, it's still in the cabin and it's still in the cockpit. And what it does is allow the pilot to monitor the pressure in the aircraft. A cabin altimeter, okay? It allows the pilot to connect it. And if you see here, we all know that basically inside a modern commercial airliner, we keep the pressure in the cabin at approximately 8,000 feet. Okay. In a basic cabin altimeter, it's connected directly. So the static port, the static input to the cabin altimeter goes straight into the cabin altimeter itself. Now, how this works, okay? When you've got your glass cockpit or you've got something, a computer automatically controlling the pressure in the cabin, inside here is the exact same as this gauge, except it doesn't have a front dial. Because it's only to measure pressure inside a cabin, the regulations state that a cabin altimeter is allowed to have errors as large as plus or minus 500 feet. Allowed to have errors plus or minus 500 feet. The other one, and a more complex one, is called the dual and differential pressure gauge. Okay, dual and differential pressure gauge. This does a couple of things, 3 things in fact. It tells me the pressure inside the cabin in feet, and also an altitude in feet. It tells me the pressure outside the aircraft in altitude in feet. And the other thing it gives you is the difference between the two in PSI. So you have to understand the differential pressure. We have the aircraft altitude in feet, the cabin altitude in feet, and it can give you the difference in pressure between the two in PSI. Oh. Okay, so remember that the three things of a differential pressure altimeter is cabin altitude in feet, aircraft altitude outside in feet, and the pressure difference between the two in a PSI. Most of you here, the ones, especially those who work on commercial airliners, when you've done like a C check, one of the things you need to do is a cabin pressurization check. Now, some of the newer systems, they've actually got a little valve. It can stop the pressure getting to the cabin altimeter or the system. It's measuring cabin pressure. But if it's got a gauge, an old-fashioned gauge, if you're doing a cabin pressurization check, you have to remove the gauge from the aircraft. If you do a pressurization check, you're putting pressure into the cabin. And if my altimeter is reading 0 feet and I put pressure in, it's going to try to go backwards. Okay. You see here, it's reading zero. If a cabin is reading 0 feet, I put pressure in, the gauge is going to try and go backwards. It's going to be mechanically damaged. So if I'm going to do a cabin pressurization check with regards cabin altimeter, it has to be removed, and most importantly, the pipelines blanked off. Okay, so for pressurization checks of the cabin, I have to remove the cabin pressure gauge and blank off any pipelines. Okay. All happy on that? Yep. Yes.
The blank to those pipelines which from which we remove the instrument, right?
Yes. So the pipelines to the back of the gauge.
Okay.
Okay. Then I forgot. Basically, the pipelines to the back of the gauge. Remember, if it's a basic cabin altimeter, it's not going to be the end of the world. But if I have a differential cabin altimeter, I've got one static vent going to the cabin. I also have one static vent going to the aircraft static system, which is open to the atmosphere. So if we didn't blank off the pipelines, I'd have a leak to atmosphere. Okay.
Okay.
Yeah, I'm not going to go through an altimeter check. You've all seen that. Right. Okay. Are we all happy on altimeter? Yep,
yes,
all happy on altimeter. Next thing we're going to look at is airspeed indicators. Okay, airspeed indicators. Again, we're all different types here. Here's a very basic one. This one here, very basic. We'll talk about this one, and then we're going to come to a more complex one. Okay, later on. Airspeed. Remember airspeed. Airspeed got to get this right. Airspeed is the flow of the air over the wing. Okay. So basically the airflow over the wing. It's not ground speed, that's something completely different. Now, gentlemen, there is a requirement for you to be able to, in accordance with the CAA and the EASA regulations, that you can are able to convert knots to miles per hour and miles per hour to knots, okay? Right. So if I'm going to go from knots, sorry, miles per hour to knots, that's the multiplication factor. That's a nightmare. You've all done the exam, so the first thing you know is it's a multiple choice exam. So if I go from knots, sorry, miles per hour to knots, it must always be a smaller number. You can see here, I'm going to multiply it by 0.868. Now, you don't have a calculator in the exam, but let's have a look at this. If I have 200 miles per hour, mph, and I want to convert it to knots, that's quite simple because it's just double that and 3 zeros, isn't it? So basically it's going to be 2 times that. So it's going to be what I reckon just off there about 172 miles per hour, approximately. So we're 172 knots. Yep. If it was 250, it's got to be again double that, 172, plus half of 86. So that is 43. I'll put 43 onto that, which will give me 5, 1 plus a 1. So basically, it'll be 250 knots. So that's the easy way. We're not going to give you 317.2 knots, miles per hour, convert that to knots. That is really, really bad. It's going to be, if you do get it, it's going to be easy figures like that. Okay? It's either going to be a full number or half a full number. And you can always get rid of one answer, because if one answer, the A, B, and C, is greater than 200, it can't be that, it must always be lower. Let's look at this one. Knots to mph. The first thing is, it's going to be greater. The multiplication factor is greater. Okay. Again, it's not going to be bad numbers. But if I go from knots to mph, it's a nice, easy conversion. Okay. Let's go from 370 knots to mph. Right. We're going to break this down into 3 little sums. 1 times 370 is 370. Yep. 0.1 of 370 is 37. And 0.05, that's half of 0.1. So it must be half of 37, which is approximately 18 and a half. We'll call it plus. So add that up. So basically that's 407 plus 38, 407 plus 38. So it'll be equals 445. Okay. So you ever get one of those conversion, that is the quickest way to do it, rather than try to do a big long multiplication. Okay, so that's, you could be asked to do speed conversion. You could be asked to do speed conversion. Okay, before we go on to looking at ASI, we've been going this over now. We'll go for a quick 10-minute break and we'll come back. Okay, gents?
Okay.
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 Quick 10-minute break and we'll come back. How are we all doing, gentlemen? Okay, we all ready to make a start?
Yes, me.
Okay, right,
Yeah.
make a start. Okay, lovely.
Oh.
Yes, Yadav.
Yes, we can start.
Oh, okay, right, lovely. Okay, right. So we're now going to look at airspeed indicators. Okay, but first thing we're going to do is look at first thing we're going to look at is what pressures are acting on my airspeed indicator. Okay, now an airspeed indicator has two pressures. Okay, but what we're trying to get is the speed of the airflow over the wing. Okay, or the basically the surface is going to provide the lift. And we have this little here, okay? Remember we said we've got two pressures. We have the static pressure, and that's that column of air above us. Look at my pen. Right, so that's the static pressure that's that column of air above us, okay? Dynamic pressure is the pressure, dynamic is speed, okay? And that's the speed of the air, okay, going across the wing, okay? So it says there that equals the total pressure, because remember, this dynamic pressure, if I put it in here, is D plus S, okay? So we've got this two here, the total pressure equals dynamic plus static, okay? Dynamic plus static. Okay, so it says here dynamic pressure is the total pressure minus static pressure. Another word for total pressure is pitot. Okay, and we now know pitot is dynamic plus static. Okay, and we put in brackets here P plus S. Okay, so my dynamic is P plus S minus static. Okay, sounds complex, but when we have a look at the gauge in a minute, it works out. Because remember, I only want the dynamic pressure. But when I look at my pitot mast, okay, my pitot head, I've got the dynamic pressure with the speed going through. But also with that dynamic pressure, okay, that dynamic pressure is made up of the speed of the aircraft and that column of air. Okay, so pitot is P plus S. Okay, but I only want this dynamic pressure. So what I'm going to try and get is the pitot to equal the dynamic. And if you look at this formula here, P plus S minus, so if I have here dynamic equals P plus S minus S, that and that cancel each other out. And that's what we're going to do inside our airspeed gauge. Okay, we're going to cancel out the static pressures. So we're only going to indicate the speed of the air across the aerofoil, the wing. So let's have a look at this. This is a basic little airspeed indicator. So now if we look at this pitot tube, okay, so, oh, it was my pointer. And we now know that pitot is dynamic plus static. The static tube is just static. So now going into here, you can now see I have dynamic plus static in the capsule. And that capsule is made of beryllium alloy. So it's quite springy, it's ductile in nature, and it's non-magnetic. But this time in the capsule itself, it doesn't have a vacuum. It has pitot pressure, okay, which is dynamic plus static. So now I've actually got the dynamic plus static pressure trying to push the capsule to expand. At the same time, I have static in the case, and that's basically trying to crush the capsule. And as the two static pressures are equal, the static going out is cancelled out. The static coming in, pushing in, is cancelled out. So all I'm left with is dynamic. And we now know dynamic, that's the airflow. Okay, that's the airflow over the wing. So we can now see it's still a differential pressure gauge, but in the capsule it's dynamic, or it's pitot pressure, and pitot is dynamic plus static. And into the case we put static, and as you now see, both static pressures cancel each other out, and I'm only left with the dynamic pressure, and that's the pressure caused by the aircraft flying through the air. So let's have a look at E-gauge. So therefore we can see now my pitot tube, okay? You've all got them in your aircraft, pitot tube. It's got a little hole at the front to allow that pitot air. So into here, we're going to have dynamic plus static in the capsule. Now we look at the next bit is my static airline. That puts static into the case. Both of them now cancel each other out, and I'm just left with the dynamic pressure moving the capsule, or expanding or contracting the capsule. And that movement goes via some linkages and ranging bars, sector gear, and moves the pointer. Okay. So gentlemen, you have to be aware that pitot pressure equals dynamic plus static. Yep. In the gauge itself, I have pitot into the capsule, static into the case, And at that point, the pitot equals dynamic, and that gives me the airflow over the wing. So it gives me the speed of the aircraft going through the air, which provides my lift. Okay, so we're all happy in the understanding of what we're measuring and how we do it. Anyone get any questions on that? No, good. Oh, who's got a question?
Not
No
yet.
question.
I can't. There's two people talking. I can't hear what you're saying. TR?
Not yet. Not yet.
No question. Okay, right, lovely. Right, so I'm going to show you a quick animation of what happens. Now we'll watch it. As the aircraft speeds up, you'll see the speed. The pitot, the dynamic plus static, will go into the case. That will expand, and there's the static all going into the case. Okay, so have a quick watch of this. Aircraft starts to increase speed. You can now see that the capsule expands via the linkages, and if it starts to slow down, it collapses because the okay. So as the aircraft speed up, that dynamic speed, the pitot, increased due to the dynamic pressure of the aircraft going through the air. The capsule expanded, and via all these linkages caused the pointer to move. So I'll just show you that again. Aircraft speeds up, more dynamic pressure, the capsule expands. Aircraft slows down, dynamic pressure less, capsule decreases. Okay, so that's the basic understanding of a airspeed indicator. Okay, airspeed indicator. So, the first thing, a basic indicator shows what's called indicated airspeed, okay? Not true airspeed. Okay, so let's look at the three different types of speed, okay? When I have an indicator, remember I said every time we get a component, we'll get an EASA Form 1 or some sort of serviceable certificate. But in pitot statics, we get two. We get a serviceable certificate and we get what's called a calibration certificate. It tells you the errors for every individual speed. Combined with pressure error, which is the manufacturer's job to get rid of, if I take into account indicated airspeed with my calibration sheet and pressure error, it becomes what's called calibrated airspeed. A lot of smaller aircraft, that's all they'll ever use. So a lot of your private aircraft, some of your helicopters, all it needs is calibrated airspeed, because they don't get very high. The higher you go, the less dense your air is, okay? And the less dense, that means you've got less molecules hitting that capsule, therefore it won't expand. So we have to take into account the density of the air. And basically, as I said, we can't measure density very easily in an aircraft. And just like the altimeter, we're going to look at temperature, compare temperature to density. Okay, so to get true airspeed, okay, true airspeed or TAS, we have to take into account air density. What we get that by taking the outside air temperature. So that there indicated air sheet is calibration sheet, pressure error, I remember I said pressure error, that's done by the designer and the manufacturer. That gives me calibrated airspeed, and for most small aircraft, that's perfectly good. But for your aircraft that are flying at 30,000 feet and flying at 600-700 knots, you need true airspeed, okay? True airspeed is taking temperature to compensate for the density of the air at higher altitudes. So please remember how to get from indicated airspeed. You need your calibration sheet, and pressure error gives me calibrated airspeed. To go from calibrated airspeed to true airspeed, I need to take into account temperature, because that's directly proportional to density.
Len,
Yes.
for this calibrated airspeed, we have to take also account of that pressure instrumentals, right?
Right. Into a sec. Right. When I get an airspeed indicator out the box from stores, okay?
Okay.
It'll come with the serviceable certificate and something called calibration sheet. So what it'll say is 100 knots, it was reading 102. 200 knots, it was reading 204. 300 knots, it was reading 299. So we know the error. So the pilot will know when he wants to fly at 300 knots, he only has to fly at 299. Okay, to take into account for that. Pressure error, remember I said there's nothing we can do as maintenance engineers about pressure error. It's all done by design. But because the air designer is taking account pressure error, we have taken into account with the pilot the calibration sheet. That means my airspeed indicator is reading what we call calibrated airspeed. So for slower aircraft and low altitude aircraft, that's all we need. Calibrated airspeed is good enough. But when I start to fly faster and higher, the density of the air changes. Okay, higher altitude, less dense air, less molecules to go into the capsule. Okay, less molecules, it won't expand as much. So we need to take into account that temperature or that density. Does that answer your question?
Okay, thanks.
Okay. So remember how we get from one speed to another. Indicated, calibration sheet, pressure error. Calibrated airspeed to true airspeed, we take into account temperature. Now we'll look at some of the markings on the gauge itself. This will be obvious to most of you. Okay. Red, you're going to die. Okay, you go into the red zone, it's the maximum limits, you die. Aircraft will fall apart. Yellow or amber is the precautionary range. Green is normal operating range. And I tell you what, gentlemen, if I give you that question right now, every single one of you would have got that right. What does green indicate in an airspeed indicator? Normal range. Amber is precautionary. Red is maximum limit. You would have all answered that question. Okay. Here's one. The next one is the white arc. Those who are helicopter boys, you will not see this. Okay. You will not see a white arc on an airspeed indicator in a helicopter for this one obvious reason. White arc indicates the range which flaps may be lowered. And as we all know, there is no flaps in a helicopter. Okay, but the helicopter boys, you still need to know it for the exam. So what do the colours indicate? Red maximum limit, danger zone. Yellow, precautionary range. Green, normal operating range. And the white is the range at which the flaps might be lowered. Okay, so please remember that. Now, okay, now, next thing we'll look at is something called an airspeed switch, It operates exactly the same as a normal airspeed indicator. It has a pitot connection to the capsule and static to the case. What it does is allow, as it says here, allow certain items to turn on or turn off at certain speeds. Okay, and if you look down here on this little diagram, you can see this rod controls that contact. And what it does, it can either make or break contacts. So when you get to a certain speed, it allows you to operate a certain system. If it goes below a certain speed, it might switch a system off. Okay, I'll give you two examples. One of the things, you have an interlock to stop you from raising the undercarriage unless you get to a certain speed. Those who are working on A320, 737s, is that correct? Anyone? Okay.
Correct.
It's correct. Thank you very much. So, even though the pilot might move the lever, electrically, it doesn't connect to anything until it gets above a certain speed. Yep. That can be, that's controlled by the airspeed switch. It's connected to the normal pitot-static system. Okay. Another one, not overly happy with this, but I'm going to tell you now, one of the things we say might be controlled by an airspeed switch is the pitot heaters. Just accept it, okay? So what system, what's the purpose of an airspeed switch? Is basically allow, without any pilot interaction, to automatically turn systems on or off at certain speeds. An example will be, as we say in that PowerPoint, pitot heater. Just remember that, okay? So what system could be controlled by an airspeed switch? As it says there, pitot heater. Now, the next thing we need to take into account is something, again, temperature compensation. Okay, temperature compensation. Remember, just like the altimeter, the capsule is made of beryllium alloy. So actually, between the temperatures, it might not expand if it's cold as much if it's cold. If it's too hot, it'll expand too much. So we're going to do something to compensate for temperature. And again, look, 15 degrees. So again, the instrument will operate correctly with no correct temperature correction at 15 degrees, okay? And it says here, we're going to use an inverse steel laminated ranging bar, okay? We're going to use a laminated inverse steel ranging bar. It's going to give us, okay, this temperature correction. So now, remember about our inverse steel? Remember, it does not expand over a wide temperature range. But if I laminate it to say copper, copper will expand and contract. So what will happen is that inverse steel laminated ranging bar will bend. So let's have a look at this here, right? So here is a little diagram of my airspeed indicator. Again, pitot, which is dynamic and static into the capsule, and static to the case. Okay, we've got a whole load of gears, and it does say there's 2 ranging bars. Okay, just from my experience, I'm going to tell you it's that ranging bar there that will bend. Okay, it's that ranging bar there that will bend. Okay, and what will happen is it's just going to bend and will cause that, because it's in what's called this banana slot, it will advance the movement when it's very, very cold. So it will move more when it's cold. And if it's cold, it will bend the opposite direction. So it will, sorry, when it's warm, it will bend the opposite direction. So it won't move the gear as much. Okay, but all you have to remember is how we do temperature compensation in an airspeed indicator, and that is a laminated inverse steel ranging bar, right?
Lynn,
That's temperature compensation done.
Lynn,
Next, yes.
like in the altimeter, there are 2 compensating
Yeah, yes,
quantities.
correct.
One is by metallic and other is in bar steel,
That's correct.
which is not laminated, right?
The inverse steel in the altimeter, the pin is not laminated. Yeah,
in the altimeter, but here is laminated.
it's
only
laminated. Yes, it is.
And here is not used the bimetallic.
No, it's just a laminated ranging bar. It's going to bend.
Okay.
This ranging bar here is going to bend in this, what we call a banana slot. So if it's very, very cold, we need it to move more. And let's say this ranging bar will bend. Let's say it bends up. So basically it advances advances the movement. When it's very, very warm, which means it's very, very soft, the ranging bar will bend the other direction, which basically means the movement is less. It won't move as much. Okay.
That in this case, bar is either it's bends or
yeah.
In the case of altimeter, no change.
No, the inverse steel. No, in the inverse steel is no change. So what we're going to have is basically this inverse steel bar is going to bend up like that, okay. Or it's going to bend up. It's going to bend down like that. So it'll either advance or retard the amount of movement. Okay, you can see that there.
Yeah.
So it'll bend. So it'll move it more if it's very cold, and it will move it less if it's very warm. Okay. Right. So just remember that it is different. The altimeter is different from any other instrument we're going to talk about. Okay. The altimeter is the U-bend, the U-spring, and inverse steel pins. Yeah. ASI, and we'll look at the VSI as well. It's a laminated inverse steel ranging bar. Okay.
And this also the same 15-degree to straight, right?
And when it's exactly, that was the next thing I was going to say. So the ranging bar is straight at
15 degrees Celsius.
15 degrees centigrade. Yep. Because that's all our instruments, when they're calibrated and manufactured, they're manufactured to be accurate at 15 degrees in accordance with the standard atmosphere. Right. If only it was just temperature compensation, it would be laughing. Okay. Unfortunately, we need to take into account what's called square law or density. Okay, we need to take into account the density of the air, because as further I go up, the less dense it's air, the less force there'll be on the capsule, and therefore it'll indicate wrong. And what we're going to do, this is what's called square law. Okay. The density change in altitude, the error is called square law. So we're going to correct square law. Okay. And there's the formula for it. Pressure equals a half rho V squared. Okay, half rho is the old Greek letter rho. Rho equals the value. Hold on. I'll just put this here. Rho equals the value of density of the air. Okay, that's what rho means. V is the square, is the velocity, the speed, and that's squared. Okay. And as it says here, as the speed doubles, the pressure increases by 4. That's what happens as you fly through the air. If every time you double the speed, the pressure increases by 4. So what would happen is your gauge would be what's called logarithmic. It wouldn't be equal spacing. So what we do, we need to compensate for square law, and that's where that banana slot comes in. Okay, so the movement, are you all happy with the difference between logarithmic and directly proportional? Here's a graph. Okay, if it's directly proportional, it goes like that. If it's logarithmic, it goes like, oh, come on. Oh. If it's logarithmic, oh, come on, give me a break. I hate technology. I've lost my arrow, hold on. So there's directly proportional, and logarithmic is like this. Okay. And you can see here it's like a bend. And look, the banana slot, which compensates for square law, that logarithmic is also bent. So here at low speeds, we don't have a great pressure change. Therefore, it doesn't move for one change in speed, the pressure, or one change in pressure, we don't get a lot of movement. Whereas up here, we need a lot more pressure to get the same amount of movement. Now, if you get asked this here, that's the square law, that's the formula. You could be asked using this formula here, okay? It says, using square law, or what would happen to the pressure inside the capsule, okay? If, I'll give you an example, if the aircraft was at 200 knots, okay, and the pressure in the capsule was, let's call it 2 psi. What would be the pressure inside the capsule if the aircraft went to 400 knots? And you can see here, it says as the speed doubles, it goes by 4. Okay, so if the speed doubles, it went from 200 to 4, it must be 4 times that. It must be 8 psi. Okay, 8 psi. What if I couldn't remember that formula? Let's go back to this half rho v squared. The half's not going to change. Yep, half's not going to change. So we'll leave that there. Were it straight, if we say we're staying at the same altitude, has the density of the air changed? No. Okay. And what you've got to do here is velocity. Let's give it 10. So 10 squared. So we'll give the density a value of 1. That doesn't change. So half times 1 is 5. 10 squared is 100. Okay. Half times 10, so half times 100, sorry, 5 times 100 equals 500. Now let's look at if it doubles. So now it's got to be, the speed is now 20. The half's still the same. We keep the density at 1 and we square it. Okay. That is now 20 squared is 400. Yeah. Times 5 gives me 2000. And you can now see the pressure has gone from, if I've doubled the speed, it was 500 at 10 knots. It's now 2000 at 20 knots. So the pressure, if the speed doubled, the pressure has changed by 4. So if you forget this bit, what happens with square law? Speed doubles, pressures increases. But if you can remember that formula, a half rho v squared, put the half, put the density of 1, and just put 2 values, you'll actually see what happens to the pressure. Okay? But if you can remember it, all well and good. So, square law. How do we correct for it? We have the banana slot, which again will make the movement logarithmic. What does square law do? If the speed of the aircraft doubles, the pressure inside the aircraft will increase by, beg your pardon, times 4. Okay. Are you all happy on square law? Yeah. Okay. We've got a couple of other errors. We've talked about that already. Indication error we've talked about is basically instrument and pressure, calibration sheet. Compressibility error. Compressibility error. Where would you get compressibility error? Let me go back to here. Here's my pipeline. Whoops. And if you notice at this point here, I have a sharp bend. And if I start to increase speed, the air starts to build up and bounce back. Okay, bounce back. And what will happen is it'll cause a blockage. So basically very, very little or slow air starts to get into the pitot, through the pitot pipelines. Therefore, my airspeed becomes wrong. And it says here compressibility is due to increased speed. The air starting to compress together. Where are you going to find that? It's going to be at the back of the pitot head, okay? Compressibility error is found at the back of the pitot head. How do we get rid of it? We can't. That's why the designers will change the bend in the pitot head to get rid of that. Density error, okay. Because our instrument's calibrated at sea level, density is square law. Square law we take into account by the banana slot. Okay. If you have a suspected problem with your airspeed indicator, you'll do a pitot-static functional. You don't have to take it out straight away. You can do a pitot-static functional check, do that, and it'll tell you whether it's good or bad. Okay, happy on any questions on airspeed indicators? No? Good. Yes.
Is there any such condition like in previously we discussed about the altimeter, like ruptures and leakage, etc.?
Okay. If that's the question, we'll just talk. We'll quick talk about it.
Okay.
Remember, it's a pressure. Again, it still works as a pressure differential gauge. Yep. Let's see now. Oh, let me come back in. Let's say now I rupture that disc. I put a massive big hole in that disc. Is the pitot going straight into the case? Tia? Yes, it is.
Yes.
Is it? Yes, it is. So therefore, if the pressure in the case is equal to the pressure in the capsule, there is no pressure difference. Agreed? And if there's no pressure difference, my airspeed indicator will read 0.
Yeah.
Yep.
Yes.
Okay. Right. Let's talk about the last basic pitot-static instrument is the vertical speed indicator. The vertical speed indicator. It gives me the rate of change of pressure. It tells me how fast I'm climbing or how fast I'm descending. Why do we need to know that? There's two main reasons. The first one is air traffic control might tell the pilot to climb from 10,000 feet to 20,000 feet at 2,000 feet per minute because of all the traffic in the area. So he needs to know how fast he's climbing. The next thing, from an engineering point of view, if I climb or dive too fast, I'm going to structurally damage or stress the airframe. So there's a maximum climb and descent rate for your aircraft so you don't structurally damage it. So that's the two main reasons why we have pitot-statics. Okay, we have the vertical speed indicator. Okay, that's why we have the vertical speed indicator. So again, it's a differential pressure gauge. But I'm going to tell you now, it only has one input, static. Okay. And we're going to figure out, I'm going to show you how we get a difference of pressure to get a differential pressure. Okay. When we look at the gauge, okay, you can see the arrow is at the 9 o'clock position. And as we go up, it'll tell me the rate of climb. And if we go down, it tells me the rate of descent. If we now look here, we now look at the three. This bit, the 20 times 100. So basically it's feet per minute times 100. So that's 2,000 feet per minute. That is the maximum rate of climb or descent allowed in the aircraft. Okay. Vertical speed indicator also has a couple of names depending on the aircraft manufacturer. Some of them call it a rock rate of climb. Okay. Some call it a rock die rate of climb and descent indicator. It's three names for the same indicator. So some of you might, depending on your aircraft, call it something slightly different. But it's the basic vertical speed indicator. Okay. Now what we watch this little video, it's a little aircraft. And if you can see here, there's my altimeter. Here's my vertical speed. Now what? See the vertical speed's climbing? And now the altimeter's starting to climb. You see that there? The vertical speed stops, but you can see that the altimeter's still climbing. That was that instrument lag. Now look here, what happens? He's climbing, he's climbing, he's climbing, and now he's starting to level out. The vertical speed indicator slowly comes down. Okay. But the altimeter didn't move very quickly. Now he's going down. The altimeter, its needle starting also to going down. altimeter stops about now. You stop, and the vertical speed indicator takes a few seconds to stay gone back to 0. Okay, so what he's indicating there, he went up and he went down. So let's look at how this system works. Okay, it only has one input. We only have one input, and that is static. Okay, so that's my static. So we can see here static goes straight into the capsule. It also goes into the case. But now you can see here, I only get a small amount of static. We have here what's called a calibrated leak, a choke, and a metering unit. It's 3 names for the same device, okay? We're going to look at it as a metering unit. Okay. So you can see here now, if I'm flying in straight and level flight and have been for several seconds, the static pressure in the capsule must equal the static pressure in the case. The capsule is at its datum width. Okay, and when it's at its datum width, it doesn't indicate a climb or descent because the static in the case and the static in the capsule are equal. Okay, as it says there, in straight and level flight, the static in here equals the static in the case. Let's look now what happens when the aircraft starts to go down. Okay, what we have to remember when the altitude goes down, pressure goes up. Okay, so the aircraft is going to descend. Instantly, the pressure increases in the capsule. But because of this calibrated leak, this metered leak, the pressure in the case only increases slowly. So now, can you see, I now have a pressure differential between the capsule and the case. Because I've now got greater pressure in the capsule than in the case, the capsule will start to expand. The capsule expands via some linkages, some gears. It starts to show a descent. Okay. Okay. When the aircraft levels out, the pressure in the capsule stops changing. The pressure in the case continues to increase. As the pressure in the case starts to increase, the pressure differential between the capsule and the case starts to decrease. And what will happen is the capsule will start to go back towards its datum position. And as it does, the needle will start to come down until it indicates 0 again. And that is what we call instrument lag. So now, again, we're going back to straight and level flight. Now, we're starting to go up. And as we now know, when altitude goes up, pressure goes down. So now the aircraft starts to go down. The pressure outside the aircraft is lower than inside the capsule and is lower than what's inside the case. So it now starts to suck the air from the capsule. It sucks the air from the capsule instantly. But the pressure inside the case reduces slower than the capsule. So now I've got a greater pressure inside the case than the capsule. The capsule starts to crush, get smaller. Via the linkages, it will indicate a climb. And it will continue to climb until it levels out. When it levels out, the pressure stops changing in the capsule, but the pressure inside the case is still higher than outside, and slowly the pressure inside the case starts to reduce. And as it reduces, the pressure differential starts to come down. The needle starts to get close to zero. When the pressure inside the case and the capsule are equal, there's no pressure differential and the needle will go back to zero. And that time taken to go from when the aircraft levels out to the vertical speed indicator stop reading a climb and going back to zero is called instrument lag. Okay, so what do we need to know about a vertical speed indicator? The pressure differential in the gauge is caused by the metering unit. Okay. Any pressure change outside the aircraft is also felt in the capsule, but there's a slower change in the case of the instrument. Therefore, we'll get a pressure differential and the capsule will expand or contract. And it's all down to that metering unit. Okay. Now, we need to talk again about density, unfortunately. We need to talk about density. And as it says there, the higher I go, the higher the increase my altitude, less dense the air. So therefore, the higher I go, the less molecules of air are in the case. Okay. Therefore, it's going to have an effect on the operation of the capsule. So what I need to do is take into account the density of the air. Okay. Because remember we said it was calibrated at sea level 15 degrees. If we're higher, the density at 30,000 feet is much less than at sea level. And if I remember rightly, if I was at 40,000 feet, the air density is a quarter of that of its sea level. So this metering unit or choke, we need to make it compensate for air density. Okay, and we're going to look at two ways to compensate for air density. The first one is the ceramic type. Okay, this is the one you're going to find in bigger, more expensive aircraft. The capillary and hole we'll probably find in more cheaper aircraft. Okay. I have a better, I think I've got a better. Right. So here's my ceramic type. This is inside the vertical speed indicator. Look again, here we go. When we said density, we can't measure density, but we can take into account density with temperature. Yeah, exactly. And we now know, look, there we've got a bimetallic strip. And we now know a bimetallic strip will bend, is straight at 15 degrees, and will open, and will bend if I increase the temperature one way, and will bend the other way when it gets colder. So let's look at the atmosphere as we know it. When I go higher, the atmosphere becomes colder. Agreed? And if I go higher, the aircraft density gets less. So now I can use this bimetallic strip to compensate for air density. If we look at the bimetallic strip, we come to the end and it's on this little plunger, okay? Little spring plunger. And what this is going to do is let the air, this, you've got two ceramic leaks, okay, two ceramic ports, but this one is connected into the instrument case itself. So here, that bit there is connected to the instrument case. You've all done aerodynamics, haven't you? Have you all done aerodynamics? Module 8? Well, most of you have. And you know how air comes in laminations. So what I want to have is the correct number or the correct density of air going into my vertical speed indicator, no matter the altitude. So what's going to happen is, if it's very, very cold, I've got less dense air. Agree with that. So what's going to happen is this bimetallic strip is going to bend inwards. So this bimetallic strip is going to bend. It's going to close off this valve. So basically, most of the air is going to go into the case because it's less dense. Let's say I now start to come down to lower levels. Okay, start to come down. The temperature of the atmosphere is going to go up. When I come down, we also know the density of the air is also going to go up. So what we can say is, as the temperature goes up, as the air density goes up, what we're going to do is gradually, this bimetallic strip will now start to bend the other way, and this plunger will start to come up, opening the valve. It opens the valve and lets a little bit of the air pressure out to allow the density to stay the same. Okay, so all you need to know on a ceramic type density compensation is it works on temperature, and the bimetallic strip will move. The higher you are, the less dense. The bimetallic strip will push the plunger in to keep the density of the air high, or keep it correct. When I start to come lower, or the temperature starts to go up, the bimetallic strip will open, allow a little bit of that air pressure to come out, keeping the density of the air the same. So my ceramic type metering unit works on temperature, and what happens is there's a bimetallic strip opening and closing a little valve, keeping the pressure or the density of the air, and my vertical speed indicator the same. Okay. And that's what it's going, that's what I would have said in that small diagram there. Okay. It says, so as the altitude increases, the temperature decreases, the valve will increase progressively close, which will force more of the pressure through the second element, i.e. into the case, keeping a constant density. The next one is what's called capillary and hole, okay, or capillary and orifice. This is it here, okay, and all that happens is the air starts to come in. Okay, as the air starts to come in, we'll look at this little capillary and orifice. If I actually look at it, it looks like this. Whoops, that's not straight. So now, as the air comes in, okay, it's got to go past this blockage in the metering unit, okay? And what we've got to think about, if I've got very, very dense air, okay, very, lots and lots and lots and lots of laminations, dense air, some of this will get caught in here and become turbulent. Turbulent air has less pressure, okay? Turbulent air has less pressure. So what will happen is some of these laminations will be lost through turbulence and we'll get, let's say we want 3. We had 4 coming in. A little bit of turbulence, we lose 1. Now, if I only have, let's say 2, it doesn't lose any here, but by the time it's funneled through this gap here, it increases, okay? So all we've got to think about is this bit here. Has a combination of holes, which have a turbulent airflow that lets at low altitudes, which loses pressure. It says here the pressure drop across the holes. The capillary will change the air pressure density, but in opposite way. A decrease in air density will increase the turbulence through the capillary, etc. So all you got to understand here is in a capillary and hole, turbulent air will actually have a drop in pressure. So basically, if I have very, very dense air, it goes through this orifice, it creates turbulence, and we lose some of that air pressure to keep the density the same. Okay. Now, I'll come back to this in a minute. All happen in the basic density compensation in a vertical speed indicator. Remember, big commercial airliners are going to be using the ceramic type, which has got the bimetallic strip. Okay. Lower you come, the more it'll open, allow some of that dense air to come out. Now, on here, in a vertical speed indicator, you have what's called something a zero adjust. It's a tiny, tiny little screw. Now I've got it back here. You can just see it here. There's a tiny little screw. Okay, you can adjust it. Please remember, gentlemen, if it's constantly reading, let's say constantly reading, okay, constantly reading 200 feet. Okay, it's the The pointer's constantly reading 200 feet. That means it's reading 200 feet over. That is a maintenance fault. We have to record it in the maintenance log. Okay, we have to record that in the maintenance log. Now, we can get rid of that because we have something called a zero adjust. This little screw, okay, this little screw, what it does, it moves this tapered screw in and out. And what it does, it lifts the base, the capsule, lifts the base, the metal sheet that the capsule's resting on. So if I was 200 feet over, I would screw it out to bring this plate down. Okay, and that's all I'm doing. But please remember, it is a maintenance task. Okay, it's a maintenance task. There's rules and regulations, and again, the specific rules for zero adjustment will be in your maintenance manual. But what we tend to say is, okay, zero adjustment is 10% of maximum rate of climb. Okay, so when I go back to my vertical speed indicator, you can see here that the maximum rate of climb is 2,000 feet per minute. Would you stop doing that? 2,000 feet per minute. So the rule is I'm allowed a maximum of 10% of 2,000 feet per minute. So now I can say 10% of 2,000 feet per minute is 200 feet. So in this case, the needle was 200 feet. It meets the regulations. So I'm allowed to do a zero adjust. I can drop it down 200 feet. If it was 6,000 feet per minute, I'm allowed 600 feet per minute. Remember, this will be recorded somewhere in your maintenance log. Okay, so we don't keep doing it.
Len,
Yes.
this 10%, 200, this also need to be entered in the maintenance log?
Yes. When you adjust it, because, okay, let's say, give you an example. The pilot says to you, today, my vertical speed indicator's overreading by 100 feet. So you adjust it. Next week, another pilot tells you it's overreading by 100 feet. It's still only 10%. You adjust it. 2 weeks later, another pilot tells you it's overreading by 10%. It's only 100 foot. You adjust it again. But in total now, you have adjusted it by 300 feet, which is greater than 10%. So that's why we record it in your maintenance log.
I mean to say, like, if it is within the 10%, it also need to be entered?
Oh, yes. Yeah.
Okay.
Because basically, if I was to say to you, even if it's 50 feet, this needle should be reading 0 on the ground on straight and level flight. It has an error. Okay. We need to get rid of that error. So any changes to make this read 0 is a fault and it needs to be recorded in the maintenance log. Okay, the gauge is still okay. If it was only 50 feet, you adjust. This is sensitive. If it was only 50 feet, it's only 50 feet. We don't need to take the gauge out. But once we've got over 200 feet of adjustment, you can see now it is the gauge must be at fault. So how it's recorded in your maintenance log will change between aircraft, but it is recorded. Okay, we're not doing legislation. We don't need to know how and where it's recorded. All you need to know, for a vertical speed, 0 adjust, the maximum permissible adjustment is 10% of the maximum rate of climb. And of course, on this gauge, it's 2,000 feet per minute, so the maximum 0 adjust is 200. If it was a gauge that said 8,000 feet per minute, the maximum 0 adjust would be 800 feet per minute. Does that answer your question?
Yes, yes.
Okay, lovely.
Above the 10% is unserviceable, right?
Yeah, above that, you should replace it. But again, it's a total of 10% as well. Okay, that's why you have to record it in the maintenance log. So how you do it in your aircraft and how you do in your company, you'll find that out. Okay, so just remember that we do have a 0 adjust, and we say it's 10% of the maximum rate of climb. Next minute, now remember I showed you that little video that even though the aircraft stopped climbing, the vertical speed indicator took several seconds to come back to 0. That is what we call instrument lag. Okay, instrument lag. Now, okay, instrument lag. We need to get rid of that, because if I'm in climbing in cloud, I need to know that when I level out, the aircraft has become level. So we need something, okay, a better vertical speed indicator, okay, and it's called an IVSI, an instantaneous vertical speed indicator, okay. It basically will give you a complete indication of climb and descent, and the gauge will move instantly. Okay, so how it works. Okay, there's my gauge, there's my capsule. We have static from the outside to the capsule, and again we have static to the case by the metering unit. So it works, this part works as a normal vertical speed indicator. The next bit, the addition, is called something called a vertical acceleration pump. And a vertical acceleration pump works on the principle of inertia. It doesn't like to change position. So let's look how it works. I'm flying along in straight and level flight, as you can see there. Okay, I'm flying along in straight and level flight. Let's say the aircraft starts to descend. Okay, the aircraft starts to descend. So the aircraft starts to go down. Yep. But we also know when we go down, pressure also starts to go up. We need to simulate this pressure change instantly. We'd said a vertical speed indicator, a basic vertical speed indicator, has instrument lag. And this is where this vertical acceleration pump gets rid of instrument lag. So now the aircraft starts to go down. The instantaneous vertical speed indicator is attached to the aircraft. That also pump, that also starts to go down. But because of inertia, the piston stays where it is. The piston stays where it is. So what we've actually done is give me strength. The piston has stayed where it is. And what we've actually done is made the cylinder like this. We've decreased the volume because the cylinder's gone down. We've decreased the volume atop of the piston. If I decrease the volume, I must be pushing air out. And that air comes out into the capsule. So it's like me going, blowing air into the capsule. The capsule expands. And the pointer instantly shows me a rate of climb. And as long as the aircraft continues to accelerate, that piston will stay where it is. As soon as the aircraft goes to constant velocity, the spring puts the piston back to the middle of the pump. And the instantaneous vertical speed indicator now operates as a normal or basic VSI. Okay? So that is what the vertical acceleration pump does. It gives that when the aircraft starts to come down. And as long as it's there, as long as it accelerates, the inertia on the pump will cause it to give that. When the speed, the climb becomes a constant velocity, it then starts to work as a normal vertical speed indicator, whereas change of pressure goes into the case by the calibrated leak and straight into the capsule. Now let's look if the aircraft starts to go up. So the aircraft goes up. We know the pressure is going to go down. So we need to simulate that pressure reduction. So now, again, if the aircraft starts to go down, the case is attached to the aircraft. That also, sorry, the case is attached to the aircraft. That also starts to go up. Okay? It goes up, but the inertia of the piston stays the same. It stays in the same position. So what's going to happen is the volume of the cylinder on top of the piston, its volume is going to increase.
B2 SUV segment में
if I increase the volume,
power to weight ratio least है.
It's like me pulling out a bicycle pump. I'm going to create a suction. And now I'm going to suck air out of the capsule, indicating the pressure being reduced. My pointer will instantly give me a decrease or a descent. And as long as the aircraft accelerates upwards, the piston will stay in the same place in the cylinder. When the aircraft stops accelerating, the piston goes back to its datum position and the vertical speed indicator operates as a normal vertical speed indicator. Okay, so this is also known as a barometer. Okay, gives me the output. Okay, is known as a barometer. So my IVSI is also known as a barometer. The principal operation is inertia of the piston in the cylinder. Okay, so if the aircraft starts to go down, it's an increase in pressure because we're going down. So basically the cylinder, the pump is going to push air out straight into the capsule to give me the correct rate of descent. If I start to climb, okay, the piston stays where it is. It causes a suction, i.e. showing the aircraft going up. Are we all happy on the instrument known as a barometer? How it works on, it's principle of inertia. Okay, and it gets rid of instrument lag. Okay, are we all happy on that?
Yes.
Anyone want to go through it again?
So Lynn, this means the main point to remember here is the time lag, which is compensated by this is acceleration.
Time lag, or what the specific name is, instrument lag. Okay, the pointer takes time to get to move through different pressure changes. And again, at low levels, higher speeds, we can't use a basic VSI. We need to use something that responds instantly. And that's that instantaneous vertical speed indicator. And the principle is the inertia of that little piston. Okay, are we all happy on that? Whoever asked that question?
Okay, so time lag is compensated by here piston, right?
Yes, yeah.
Oh, thank you.
Or the instrument lag. The specific word is instrument lag. I know you call it time, but it's the instrument lag. Yeah.
Yeah.
One last or two last things. Okay. Let's talk about serviceability. Now, if most of you, have you all done line work before? Yeah. And we all know pilots like to tell you what's wrong, and they also like to tell you how to fix it. And normally, the pilot gives us a fault, we go and check it first. We do a functional check of the system. The one component you've really got to take the pilot's word is if the IVSI is not working correctly. We cannot fully check out an IVSI on the ground. We can do what's called a leak and sense check. We can put pressure in and we can check that the capsule of the case is leaking. Agree with that? What we can't check is this piston going up and down, because we can't do that vertical movement, and not unless you're a very big bench presser. So if the pilot was to come back and say, my IVSI responded but slowly, it tells you two things. One, it was acting as a VSI because it was responding but doing it slowly. So basically it tells you it's not working as an IVSI. So basically the piston isn't working. We can't test that in the ground. So if the pilot comes back and says his IVSI wasn't working correctly, it was just working slowly, i.e. working as a basic vertical speed indicator, you have to take his word for it. Okay, so if the pilot says that, all you can do is take it out, put a new one in. Okay. And one last thing for today, gentlemen, is temperature compensation. Okay, I haven't got a picture for it, but temperature compensation of VSI is laminated invar steel invar steel ranging bar. Okay, so temperature compensation of a VSI is a laminated ranging bar. So let me just talk about temperature compensation again. In an altimeter, it's a bimetallic U-spring and invar steel pins. In a ASI, in a VSI, it's a laminated invar steel ranging bar. So the only one it's not a laminated invar steel ranging bar is the altimeter. Okay, are we all happy on that? Yep.
Len, in
Yes.
the book, there is nothing mentioned. It's laminated. It's only ranging bar is made of bimetallic of invar steel and brass to
That's what I
compensate.
said. So it's a laminated invar steel ranging bar then, isn't it? It's a lamination of invar steel and brass. Yep.
Is there mention in the book?
It should be somewhere.
I couldn't find here. That's why.
It's somewhere in the book. As I said, I've only got my old notes here. There we go. Temperature compensation. In common with other capsule operated instruments. Okay. It says here, as other instruments, the ranging bar is bimetallic of invar steel and brass. Okay, so it is in the book. It's just about, it says the typical VSI, just before we do density compensation. Okay, it's in the book. Okay, so it's the page before density compensation. So, a couple of things I want to just highlight before we go for today. Inputs. I might go back to this. There we go. Just look at this basic system, okay? As you can see, here's my static. And static goes to all instruments. So if you can remember the phrase, all instruments static, and pitot only goes to the ASI, okay? How we get, and all three are pressure differential gauges. How do we get the pressure difference in an ASI? We put pitot and static to the capsule and static to the case. The two statics cancel each other out and I get my dynamic speed, the speed of the air over the wing. My altimeter, I have static to the case, but this time the capsules have zero or vacuum inside it, and that's what gives me my differential pressure, the difference between the static pressure in the case and a vacuum. And in my VSI, we only have a static input, but static goes straight to the case. Sorry, static goes straight to the capsule and to the case via a calibrated leak, okay, or metering unit. Okay. Any questions on what we have covered today, gentlemen? I know now that must be nearly 10 o'clock your time. I know it's late. Now, I have given you some sheets. I don't expect you to do them tonight because you're about to go to bed. I think some of you got work in the morning. But when you get a chance to go through the sheet, okay? I'll find the sheet. I'll find the sheet. Where's my sheets? There we go. Let's see avionics. When you go through the sheets, I'll find my paper. How much the paper gone? Let's see avionics. Oh, let me just go into. Hold on. We're back with you in a second, gentlemen. Hold on. Load up, load up, load up. If you look at the question, if you've got the question sheets there, I've actually broken it down into basic chapters, okay? We have done up to today up to question, you go. We've done up to question 61, okay? A lot of questions, I don't expect you, but if you get a chance, use them. If you can't do it, don't worry. But over the night, you got this weekend. We're not getting any study this weekend. So if you can't do it, I understand, because you've got to sleep and you've got to work. But when you get time off, or if you're not getting anything on at the weekend, Saturday, Sunday, maybe have a go at some of the questions, okay? Maybe have a go at some of the questions, okay? It will help you revise, okay? So, gentlemen, I know it's nearly 10 o'clock where you are. Have a read at your notes, okay? Or tomorrow, when we come back in, any questions, we'll go through that first thing in the instruction before we carry on. Okay, are you all happy with that, gentlemen? Can you put your little hands up on your screen that you're all happy?
Yeah, we are happy.
Yes.
Okay. Well, gentlemen, it's been a pleasure today. Okay, go and get some sleep. I take it a lot of you are working tomorrow morning, or anyone working night shift?
No, morning, sir.
Mornings, okay. Right. I have finished with you today, gentlemen. Go and get some sleep. Have a good night. Okay.
Good night.
And I will see you tomorrow.
Sure.
Yeah, good night.
Okay, good night, gentlemen. And I'll see you tomorrow.
Okay.
Bye-bye. Okay, good night.
Good night. Bye-bye.